When the James Webb Space Telescope unfolded its golden mirrors in July 2022, astronomers held their breath. For the first time, humanity had built an instrument capable of seeing directly into the first few 100 million years after the Big Bang, a window so distant that light from that era has been stretched into infrared wavelengths by cosmic expansion. The expectation was simple. Webb would capture the universe in its infancy, filled with faint, disorganized proto-galaxies barely starting to form their first stars. Instead, what it found was profoundly unsettling. The telescope's deep-field images revealed massive, luminous galaxies existing only 300 million years after the Big Bang. They were too bright, too structured, and too old for their age. These objects appeared to contain as many stars as the Milky Way, a system that took our own universe nearly 14 billion years to build. The implication was staggering. Galaxies were forming 10 times faster than theory allowed. For decades, cosmology had relied on the ΛCDM model, lambda cold dark matter, the foundation of modern astrophysics. It describes a universe governed by dark energy that accelerates expansion and dark matter that seeds gravitational structures. According to this model, galaxies form hierarchically. Small systems merge into larger ones over billions of years. JWST's discovery violated this gradual process. The data suggested that mature, massive galaxies existed when the universe was barely 2% of its current age. That realization sent shockwaves through the scientific community. Research papers appeared within weeks. Massive galaxy candidates at redshift Z10, too big too early, challenging the hierarchical model. Yet this was not a denial of the Big Bang itself. The crisis was subtler. The mechanisms of cosmic evolution seemed incomplete. Something fundamental about how matter cooled, collapsed, and ignited into stars was missing from our equations. Before Webb, the Hubble Space Telescope had already pushed observational limits to redshift 8, roughly 600 million years after the Big Bang. Hubble's galaxies appeared tiny and irregular, exactly as the standard model predicted. But Webb's infrared vision, especially through instruments like NIRCam and NIRSpec, pushed beyond that barrier to redshifts of 13 and even 14, about 300 million years post-origin. And there, to the astonishment of astronomers worldwide, were galaxies emitting light as powerful as modern spirals. To grasp why this was shocking, one must recall how galaxies are supposed to form. After the Big Bang, the universe was a nearly uniform sea of hydrogen, helium, and dark matter. Over time, dark matter clumped under gravity, forming invisible halos. Gas fell into these halos, cooled, and began to condense into stars. This process was thought to take hundreds of millions of years, limited by how quickly hydrogen could radiate heat away. Stars then merged into small galaxies, which themselves collided and combined to form larger systems, a slow cosmic ladder of construction. But the galaxies JWST observed did not fit that ladder. Their brightness implied enormous stellar mass, and their ages implied impossibly fast formation. Either star formation efficiency was far higher than expected, or our understanding of cosmic time itself, how redshift relates to age, was flawed. JWST measures not distance but light stretching. The farther the light travels, the more it shifts toward the red end of the spectrum, a direct result of the expanding universe. High redshift means a great distance and ancient light. But these estimates can be uncertain. Many of the early galaxies were identified photometrically, based on their colors across filters, rather than detailed spectra. Later spectroscopic observations confirmed some but not all of these redshifts. Even after the correction, the puzzle remained. Objects like Sears 93316 and Galaxies 12 seem to contain more than 10 billion solar masses in stars at a redshift of 11. To assemble such a mass in so little time, their star formation rates would have to be 50 to 100 times faster than that of the Milky Way today. Dr. Erica Nelson of the University of Colorado described the discovery as like finding a fully grown adult in the maternity ward. The implications extended beyond one telescope or one observation. If galaxies could grow this massive so early, it would rewrite the physics of dark matter, gas cooling, and feedback mechanisms. It could also force us to reconsider the universe's initial conditions. Some cosmologists propose that perhaps dark matter particles interacted slightly more strongly than the cold assumption implies, creating earlier clumping. Others suggested an exotic energy field, sometimes called early dark energy, might have briefly accelerated structure formation before fading away. There were even discussions that primordial black holes, remnants of the earliest cosmic fluctuations, could have acted as seeds for these giant galaxies. Amid the excitement, scientists were cautious. Every revolutionary telescope has first returned results that seem impossible. The same happened when Hubble first imaged distant supernovae, or when COBE and WMAP mapped the cosmic microwave background. Anomalies are the engine of progress. JWST's data may eventually prove less shocking as models improve, but for now, it has exposed a blind spot in our cosmic narrative. Some of these galaxies could turn out to be less massive than assumed, or perhaps their brightness was magnified by gravitational lensing, light warped by intervening matter. Yet each explanation adds to our understanding of how dynamic and diverse the early cosmos was. Even as the initial frenzy settled, Webb continued to observe new targets. Some of the earliest impossible galaxies were reclassified, their redshifts reduced, but others have since emerged with equally perplexing properties. The cycle of discovery and doubt continues. The truth that remains undeniable is that the first billion years of the universe were far more complex than our textbooks suggested. Webb did not destroy cosmology, it refined it. It reminded humanity that even the most elegant theories are only temporary maps, and that the universe is not obliged to follow our equations. The discovery of massive early galaxies is not just a technical anomaly, it is a philosophical turning point. It challenges how we think about time, growth, and cosmic causality. The night sky is not a static archive, but a living history, where light billions of years old can overturn ideas forged yesterday. JWST has revealed that the cosmos is more efficient, more intricate, and perhaps more unpredictable than anyone imagined. Science thrives on that tension between what we expect and what we find. In that sense, the too big, too early galaxies are not contradictions, they are invitations. They compel us to re-examine how stars ignite, how matter organizes, and how reality itself evolves. As Webb continues to stare deeper into the infrared, humanity is not merely seeing its past, it is watching its understanding of existence unfold, one photon at a time. After the first surprise of massive galaxies, scientists began revisiting the basic blueprint of how the universe was supposed to grow. According to standard cosmology, the first few 100,000 years after the Big Bang were relatively simple. Matter and radiation were mixed together in a hot, uniform plasma. When the universe cooled enough for electrons to bind with protons, light decoupled from matter and began its long journey through space. This event, called recombination, created the cosmic microwave background, the oldest light we can see. For almost 400 million years after that moment, the cosmos entered a long period known as the cosmic dark ages. There were no stars yet, no galaxies, and almost no visible light, only the faint glow of residual radiation from the Big Bang itself. During this darkness, gravity quietly sculpted the invisible scaffolding of the cosmos. Dark matter, which does not interact with light, began clumping together under its own gravity. These clumps formed halos, invisible spheres where ordinary gas could later collect. It was inside these dark matter halos that the first stars were expected to form. The cooling of hydrogen gas, however, was painfully slow. Without heavy elements to help radiate heat, the gas remained hot and diffuse. Theoretical models predicted that the first stars, called population 3 stars, would ignite roughly 100 to 200 million years after the Big Bang. These were not like any stars we know today. They were enormous, hundreds of times more massive than the Sun, and burned through their fuel in only a few million years. When they exploded as supernovae, they filled the universe with heavier elements like carbon, oxygen, and iron, making future generations of stars and planets possible. The standard timeline built from this logic is elegant and consistent. Small halos host the first stars. These halos merge to form larger protogalaxies. Over time, those galaxies collide and grow into the grand spiral and elliptical structures we observe today. Everything in this chain depends on predictable cooling rates, gravitational collapse, and feedback from the first supernovae. But when Webb looked deep into the early cosmos, it saw galaxies that seemed to skip several of these steps. Some of the systems it captured at redshifts above 10 already had complex structures, mature star populations, and even dust, which should have taken hundreds of millions of years of stellar evolution to produce. Astronomers first questioned the measurements. Could Webb have mistaken nearby dusty galaxies for distant young ones? Photometric redshifts rely on how light drops out of certain filters as it stretches with distance. In theory, this can confuse a very red local galaxy with a faraway ancient one. Yet as more spectroscopic confirmations arrived, the evidence only grew stronger. These were indeed ancient galaxies, but somehow they contained more mass and complexity than anyone expected. If this evidence holds, it means that the first dark matter halos must have collapsed earlier, perhaps even before theoretical models allow. That would require the density fluctuations seeded in the early universe to be stronger than the Planck satellite data suggests. It would also demand that baryonic matter, the normal gas that forms stars, cooled and condensed much faster. To make that possible, some researchers have explored the idea of exotic cooling channels, including molecular hydrogen forming more efficiently, or even interactions with dark matter that allow heat to leak away faster. Others have pointed to primordial magnetic fields, which could have influenced the dynamics of early gas clouds, compressing them into stars more quickly. Webb's discovery also touched a long-standing debate about the nature of time in cosmology. When we observe a galaxy at redshift 13, we are not just looking far away. We are seeing the universe when it was only a few 100 million years old. Yet the processes required to build a galaxy that large, collecting gas, forming stars, recycling materials through supernovae, would need roughly that much time or more. It is as if these galaxies were born almost instantaneously after the Big Bang. This raises an uncomfortable possibility that our translation from redshift to cosmic time may not be as precise as assumed. Small changes in the rate of expansion at early epochs could dramatically shift our estimates of age. This question ties directly to one of modern cosmology's greatest puzzles: the Hubble tension. Different methods of measuring the universe's expansion rate yield slightly different values. Observations of the early universe, such as those from the Planck satellite, suggest a slower expansion, while measurements of the nearby universe using supernovae and Cepheid variables suggest a faster one. If the early cosmos expanded faster for a brief period, as some new models propose, that could have allowed matter to condense into galaxies earlier, resolving part of the mystery. In this view, JWST may have just provided observational evidence of that early acceleration. Even within the established ΛCDM framework, however, there are plausible ways to explain these rapid formations. The efficiency of star formation in the early universe could have been much higher than what we see today. When gas is denser and more pristine, stars can form in bursts that convert a large fraction of material into light very quickly. This would make galaxies appear older and more massive than they are. Another possibility involves the role of mergers. In a dense cosmic environment, early galaxies may have collided far more frequently, merging their stars and gas in short timescales, producing temporary overluminosity that Webb detected. Still, the simplest conclusion remains that our current picture is incomplete. JWST is revealing the universe not as a calm progression, but as a turbulent, rapidly evolving system where structure emerges with astonishing speed. In its deep field images, we see not a gentle dawn, but an explosive sunrise. Every bright dot in those fields is a record of matter reorganizing itself against all expectations. The philosophical weight of this discovery is difficult to overstate. Humanity's understanding of cosmic history has always depended on the idea of gradualism, the notion that the same physical laws slowly shape the universe across vast timescales. But these early galaxies challenge that rhythm. They suggest that creation itself might be punctuated, occurring in brief moments of extreme efficiency. The universe may not evolve like a slow tide, but like a heartbeat, with sudden bursts of formation followed by long, quiet phases. In the months following Webb's first release, new studies focused on refining mass estimates. Many astronomers now use more sophisticated spectral energy distribution models that account for the effects of young, hot stars and interstellar dust. Some of the initially reported galaxies may indeed be less massive once those corrections are applied. Yet even the lower limits remain surprising. Galaxies with 1 billion solar masses of stars existed within the first 500 million years, and that fact alone demands explanation. The data also show that the early universe was far from uniform. Regions of space that formed stars early created radiation that rionized the surrounding hydrogen, carving transparent bubbles in an otherwise opaque cosmos. These bubbles expanded and merged, transforming the fog of neutral gas into the clear intergalactic medium we see today. JWST's infrared vision allows astronomers to watch this transition in progress. The galaxies responsible for rionization appear compact, but extremely bright in ultraviolet light, suggesting intense bursts of star formation. Their collective energy reshaped the cosmos itself. Each of these findings adds a layer to the mystery rather than resolving it. Yet this is what makes the story scientifically rich. The telescope is not disproving cosmology. It is revealing where our approximations fail. Just as the discovery of cosmic acceleration forced us to accept dark energy, the discovery of massive early galaxies may push us to rethink how structure forms. Perhaps the physics of baryons in the early universe behaved differently under extreme conditions of temperature and density. Perhaps the cosmological constant we use to describe dark energy hides a more dynamic component that influenced early structure growth. Whatever the eventual answer, Webb's observations remind scientists that reality is not obliged to conform to elegance. The cosmos is not designed for our mathematical convenience. It is messy, intricate, and alive with surprises. Every photon captured by Webb is a relic from a time when physics was still writing its first chapters, and each anomaly is a clue pointing to new understanding. The story of these ancient galaxies is far from over. As data from longer exposures and more refined spectroscopic instruments arrive, astronomers will be able to measure chemical compositions, rotation curves, and star formation histories with greater accuracy. These measurements will tell us whether the early galaxies truly defy the laws we know or simply reveal aspects we had overlooked. In the meantime, the night sky continues to whisper that the universe is older in spirit than in age, and that the first light may still hold secrets deeper than time itself. As the first generations of stars ignited, the universe began to change in ways both violent and beautiful. What had once been a silent ocean of neutral hydrogen transformed into a luminous web of radiation and structure. This period, known as the Epoch of Rionization, marks one of the most dramatic transitions in cosmic history. It is the bridge between the Dark Ages and the transparent cosmos we now observe. When those ancient stars released ultraviolet light, they started to strip electrons from the surrounding hydrogen atoms, rionizing the intergalactic medium. The fog that had hidden the early universe slowly cleared, and light could finally travel freely across space. The physics behind this transformation is intricate. Each massive star that formed in the first galaxies burned hot and bright, emitting radiation energetic enough to ionize hydrogen. But these stars did not live long. Their deaths as supernovae blasted surrounding gas outward, creating turbulent pockets of space filled with metals and cosmic dust. Over time, the combined radiation from millions of such stars carved out enormous bubbles of ionized gas. These bubbles expanded and merged until the entire universe became transparent. Observing this process in detail is one of JWST's primary missions. With its infrared sensitivity, it can detect the faint red-shifted signatures of early star-forming galaxies that powered reionization. The timing of reionization has always been one of the key mysteries in cosmology. Based on observations from the Planck satellite and quasar spectra, scientists believe that the process began around 400 million years after the Big Bang, and was mostly complete by 1 billion years. But the presence of massive galaxies at earlier epochs implies that reionization might have started sooner. If stars and galaxies were already forming at redshifts above 10, then the universe could have become transparent far earlier than predicted. This possibility raises fundamental questions about how quickly matter organized itself and how feedback from radiation shaped future evolution. Feedback is the cosmic conversation between creation and destruction. Every time a star forms, it releases energy that can either trigger or suppress more star formation nearby. Supernova explosions enrich space with heavy elements, but also heat and disperse the surrounding gas, preventing further collapse. In the early universe, this feedback was far more extreme. The first stars were so massive that their radiation likely sterilized their immediate neighborhoods, halting local star formation for millions of years. Yet across the vastness of space, new halos continued to gather matter, forming fresh pockets where the cycle began again. This dance of ignition and quenching defined the pace of cosmic evolution. JWST's images reveal this tension vividly. Some of the earliest galaxies appear small and compact, packed with young blue stars, while others show extended halos glowing in ionized hydrogen. These are snapshots of feedback in action. The energy released by intense star formation escapes through channels in the gas, illuminating the surrounding medium like cosmic lanterns. In some cases, this radiation may even escape into intergalactic space, contributing directly to ionization. The telescope's NIR-SPEC instrument can detect specific spectral lines, such as Lyman alpha and hydrogen beta, that trace these interactions. By measuring how these lines are shifted and scattered, astronomers can reconstruct the temperature, density, and composition of gas in the early universe. Ionization was not uniform. It occurred in patches, like islands of light expanding across a dark sea. Regions near the first galaxies cleared first, while others remained opaque for hundreds of millions of years. The resulting structure resembles a cosmic foam, with glowing walls of ionized gas surrounding pockets of neutral hydrogen. This patchiness is now being studied through advanced simulations that combine dark matter physics, gas dynamics, and radiative transfer. Webb's observations are helping calibrate these models by providing real data from the relevant era. The goal is to understand how many stars and how much radiation were required to ionize the entire cosmos. The story of ionization is also the story of black holes. As some of the first massive stars died, their cores collapsed into black holes that began accreting gas. These early black holes may have grown rapidly, forming the seeds of the supermassive black holes we find at the centers of galaxies today. Quasars, extremely luminous objects powered by accreting black holes, are already observed less than 1 billion years after the Big Bang. Their existence suggests that black holes could form and grow even faster than galaxies. Some theories propose that black holes, not stars, may have been the dominant source of radiation during certain stages of reionization. If that is true, then the early universe was shaped as much by gravity's darkness as by starlight. One particularly intriguing idea involves dark matter itself. While traditionally considered inert, some models allow dark matter particles to annihilate or decay, releasing energy that could influence reionization. If even a small fraction of dark matter behaved this way, it could preheat the cosmic gas, changing when and how the first stars formed. JWST's precision allows scientists to look for subtle spectral fingerprints of such exotic processes. So far, no clear signal has been found, but the search continues. Understanding ionization is crucial for more than historical curiosity. The structure of the modern universe, galaxies, clusters, and voids, depends on how the early gas cooled and ionized. Ionization affected the pressure and temperature of the intergalactic medium, which in turn controlled how easily galaxies could accrete new material. In a sense, it set the cosmic weather conditions for everything that followed. If the early universe became ionized too quickly, small galaxies might have been starved of gas, explaining why we see fewer dwarf galaxies today than simulations predict. This phenomenon, known as the missing satellites problem, could therefore be a fossil trace of ionization itself. As Webb peers deeper, it also observes the chemical fingerprints of early stars. Elements like carbon, oxygen, and silicon appear in unexpected abundances, suggesting that the first stellar generations enriched space more efficiently than predicted. Some of this may result from pair instability supernovae, explosions so energetic that they completely disrupt their parent stars, leaving no black hole behind. These cataclysmic events release vast amounts of heavy elements into the surrounding medium, enabling rapid cooling and the next wave of star formation. Each explosion was a spark in the grand chain of cosmic evolution. The reionization era also introduces an emotional paradox. We often imagine the early universe as simple and primitive, a blank canvas waiting for complexity to emerge. In reality, it was already a place of extreme diversity, violence, and creativity. Stars lived and died in quick succession. Galaxies collided and merged. Black holes fed on matter, and the very texture of space was rewritten by radiation. To look at that epoch through JWST's golden mirrors is to see the universe in the act of becoming aware of itself. This awareness is not poetic exaggeration, but a reflection of science itself. Every time Webb captures a spectrum from a galaxy 13 billion light-years away, it adds a data point to the story of how matter learned to shine. It reveals the continuity between the physical and the philosophical, the realization that we are made of the same atoms that once illuminated the first dawn. The light that left those galaxies before Earth existed now enters our detectors, teaching us how everything began. The reionization era also reveals something profound about limits. For decades, cosmology treated the early universe as a simple boundary condition, a smooth starting point for later complexity. Now we see that the beginning was anything but smooth. It was full of turbulence, asymmetry, and rapid transformation. The first light was not a gentle sunrise, but a storm of creation. This realization changes how scientists approach the fundamental equations of structure formation. It suggests that linear models and averaged parameters are no longer enough. We need dynamic, nonlinear frameworks that can capture the chaos of real cosmic evolution. Webb's continuing mission aims to measure reionization directly by mapping the distribution of galaxies at different redshifts. Each image is a slice of time, showing how the proportion of ionized to neutral gas evolves. Combined with future observatories like the Square Kilometre Array, which will detect the faint radio glow of neutral hydrogen, these observations will produce a three-dimensional map of the cosmic dawn. When that map is complete, humanity will, for the first time, hold a detailed record of how the darkness lifted and the modern universe emerged. Every discovery seems to deepen, rather than end the mystery. We now know that galaxies formed earlier, black holes grew faster, and stars burned brighter than we thought possible. Yet we also know that these extremes fit within a deeper order, one that still obeys the same physical principles written in the first moments after the Big Bang. The universe is not chaotic, it is exuberant. It experiments within the rules it created, producing beauty out of constraint. In the end, the reionization era stands as a reminder that illumination always comes from struggle. The light that freed the cosmos from darkness was born from collapse, from the gravitational pull that crushed gas into stars. In those violent beginnings lies the same pattern that shapes every scale of existence: pressure, release, and transformation. The Webb telescope is not merely observing this process, it is participating in it. Every image it captures adds to the sum of human understanding, another small act of reionization in the realm of thought. The universe became transparent once through light. It becomes transparent again through knowledge. When the first galaxies took shape, something else was growing at their centers, something that would one day outshine the combined light of billions of stars. Black holes are often thought of as the endpoints of stellar life, but in the early universe, they may have been among the first actors on stage. Their existence challenges the linear idea that stars came first and black holes later. Webb's recent observations have begun to reveal compact sources of infrared emission in galaxies less than 1 billion years old. Emissions that may come from accreting black holes already millions or even hundreds of millions of times more massive than the Sun. This discovery creates another paradox. According to classical theory, it takes time for a black hole to grow. Even if a massive star collapses directly into a black hole, accreting matter at the Eddington limit, the maximum rate before radiation pressure pushes material away, it would need hundreds of millions of years to reach the supermassive scales seen in quasars at redshifts beyond 7. Yet those quasars exist. Their light, captured by Webb and by ground-based telescopes such as Keck and Subaru, comes from an era when the universe was less than 800 million years old. To reach that mass so quickly, something unusual must have happened. One possibility is that the first black holes did not form from stars at all. Instead, they might have emerged directly from collapsing gas clouds in the early halos. If a primordial cloud avoided fragmentation, meaning it did not break into smaller clumps that form stars, gravity could pull it inward as a single body. In the absence of cooling metals, such a collapse would be almost isothermal, maintaining high temperatures and preventing early star formation. Under those conditions, the cloud could collapse straight into a black hole weighing tens of thousands of solar masses. This direct collapse scenario has gained strong support because it naturally explains the existence of massive black holes so early. Another idea involves runaway collisions inside the dense cores of the first stellar clusters. In environments where gas and stars are packed tightly, massive stars can merge before exploding, creating a single object hundreds or thousands of times heavier than the Sun. When such an object collapses, it forms an intermediate mass black hole that can serve as the seed for later supermassive growth. Once established, these seeds can accrete gas rapidly if the surrounding halo is dense and cool enough. The gravitational potential wells of early galaxies were deep, and gas infall from cosmic filaments provided a constant supply of material. Under those circumstances, accretion could exceed the Eddington rate temporarily, allowing exponential growth. JWST's spectroscopic data have added clues. In several early galaxies, astronomers detected emission lines characteristic of high-energy ionization that cannot be explained by stellar radiation alone. The ratios of lines such as He21640 angstrom and Ni53426 angstrom suggest the presence of active galactic nuclei, compact, accreting black holes surrounded by hot plasma. In some cases, the observed luminosities imply central engines of millions of solar masses existing just 500 million years after the Big Bang. These galaxies are small, perhaps only a few thousand light-years across, yet they host black holes that dominate their total energy output. The existence of such engines has far-reaching implications. Black holes are not merely consumers of matter, they are also creators of structure. Their accretion disks generate intense radiation and powerful jets that can regulate star formation in their host galaxies. When the central black hole feeds, it can heat or expel surrounding gas, quenching further star formation for a time. This feedback process shapes the size and morphology of galaxies, linking the growth of the black hole with the growth of its host. A relationship we still observe today as the M-sigma correlation, where the mass of the central black hole scales with the velocity dispersion of the surrounding stars. The surprise is how early this coevolution seems to begin. In the modern universe, such regulation occurs in massive ellipticals, billions of years after formation, but JWST is showing hints of the same mechanism when the cosmos was still in its infancy. It suggests that the seeds of the galaxy-black hole relationship were planted almost immediately, perhaps even driving the very efficiency that puzzles cosmologists. If black holes were injecting energy into their environments from the start, they could have accelerated the recycling of gas and metals, leading to rapid galaxy maturation. Another possibility is that early black holes served as gravitational anchors for structure formation itself. Simulations show that a single massive black hole can stabilize a small galaxy, concentrating gas toward the center and igniting bursts of star formation. In this view, galaxies did not create black holes. Black holes created galaxies. Webb's observations of compact, luminous cores in young systems seem consistent with this picture. The central regions shine in mid-infrared wavelengths, where heated dust re-emits absorbed energy, a signature typical of active nuclei. The feeding habits of these black holes are also under scrutiny. To grow so quickly, they must have accreted matter continuously, perhaps aided by dense inflows along cosmic filaments. In the early universe, gas streams were cold and unshocked, flowing directly into halos without forming stable disks. Such cold accretion could deliver enormous amounts of fuel to the central regions, allowing black holes to maintain high accretion rates. This process would also explain why early galaxies appear clumpy and irregular in Webb's images. The inflowing material creates turbulence and asymmetry while feeding the central engine. The radiation from accreting black holes contributed to reionization just as starlight did. High-energy X-rays from these sources can travel much farther than ultraviolet photons, heating large volumes of the intergalactic medium. This preheating would have influenced how and when the first galaxies formed, potentially smoothing temperature variations and altering the 21-centimeter signal of neutral hydrogen that future radio telescopes will detect. If confirmed, it means that black holes were active participants in shaping the transparency of the cosmos, not just passive byproducts of stellar evolution. Yet despite their destructive power, black holes also act as cosmic archivists. The material they swallow leaves behind precise imprints in radiation. The variability of their accretion light curves encodes information about the geometry and composition of surrounding gas. JWST's high-resolution spectroscopy can detect these subtle variations across wavelengths, turning each early active galaxy into a laboratory for extreme physics. In particular, measuring how quickly emission lines broaden over time helps estimate the mass of the central black hole, data essential for tracing its growth history. The theoretical landscape is evolving alongside the observations. New cosmological simulations, such as illustrious TNG and Renaissance, are being updated with parameters calibrated to Webb's findings. These models suggest that early black holes could have grown through a combination of direct collapse, rapid accretion, and mergers. When galaxies collided, which happened frequently in the dense early cosmos, their central black holes merged as well, releasing gravitational waves strong enough to shake space-time itself. Future missions like LISA, the Laser Interferometer Space Antenna, will be able to detect these ripples, providing another window into how the first massive black holes formed. But perhaps the most intriguing question concerns the nature of the seeds themselves. Could some of them predate galaxies entirely? Certain cosmological models predict that small black holes might have formed directly from density fluctuations in the first fractions of a second after the Big Bang. These primordial black holes could range from asteroid mass to solar mass scales. If even a small fraction survived, they might have served as the gravitational nuclei around which early galaxies assembled. Observational hints remain inconclusive, but Webb's data on compact, faint sources at extreme redshifts could soon test this possibility. The existence of early supermassive black holes also forces a reconsideration of dark matter's role. If dark matter interacts weakly with ordinary matter through gravitational capture, it might have accelerated the growth of early seeds. Some theories propose that black holes can accrete dark matter directly, forming dense spikes of invisible mass that enhance their gravitational influence. This would make galaxies more compact and explain why some early systems appear so tightly bound. While these ideas remain speculative, they demonstrate how Webb's observations are pushing theoretical physics to explore new territory. Behind all the technical details lies a profound shift in perspective. For decades, cosmology depicted black holes as endpoints, the silent remains of stellar collapse. Now they appear as engines of creation, shaping light, matter, and even time itself. Their gravity organizes chaos into structure. Their radiation transforms darkness into illumination. In studying them, scientists are not merely cataloging cosmic anomalies. They are tracing the flow of causality back to its source. Each observation Webb sends back is a dialogue between human curiosity and cosmic memory. The light it collects has crossed space for billions of years, carrying with it the story of how the universe built itself from nothing but gravity and heat. When astronomers decode that light, they participate in the same process of feedback and reflection that shaped the first galaxies. Knowledge itself becomes a continuation of cosmic evolution, the universe observing its own beginnings through us. By the time the first billion years had passed, the universe already looked strangely familiar. Not the diffuse fog predicted by early simulations, but a structured cosmos filled with luminous islands of stars and galaxies. What Webb has revealed is not merely an observational surprise. It is a conceptual fracture in the foundations of modern cosmology. The lambda cold dark matter model, once thought unassailable, suddenly appears incomplete. Lambda, CDM, shorthand for lambda cold dark matter, has long been the backbone of cosmic theory. It describes a universe dominated by dark energy, represented by lambda, the cosmological constant, and cold, slow-moving dark matter that clumps under gravity to form the scaffolding of galaxies. The model elegantly reproduces the cosmic microwave background, large-scale structure, and expansion history. Yet the early galaxies that Webb observes are too massive, too bright, and too evolved to fit comfortably within this framework. The architecture of the cosmos seems to have assembled faster than the equations allow. At the heart of the problem lies time itself. The ΛCDM timeline gives matter only a few 100 million years to collapse into stars and galaxies after recombination. Cooling, fragmentation, and star formation should have been slow, regulated by atomic processes and the expansion rate. Instead, Webb's images show mature systems already glowing with heavy elements and complex structures. Either the formation rate was vastly underestimated, or some new physics accelerated it. One idea is that the nature of dark matter might not be as cold as we assumed. In ΛCDM, dark matter particles move sluggishly, forming dense clumps that merge hierarchically to build larger halos. But if dark matter were slightly warmer, consisting of lighter, faster-moving particles, it could smooth out small-scale structure and allow larger systems to form earlier. Another alternative is self-interacting dark matter, where particles collide and exchange momentum. Such interactions could redistribute energy within halos, hastening the collapse of gas in their centers. Webb's data might become the first indirect probe of these invisible interactions. Others propose that the cosmological constant lambda is not truly constant. If dark energy varied with time, stronger in the early universe and weaker later, the expansion rate could differ from what current models predict. This might resolve the long-standing Hubble tension, the discrepancy between local and early universe measurements of the expansion rate. A variable dark energy field, sometimes called quintessence, could momentarily slow expansion during the first few 100 million years, allowing matter to clump faster. Yet such modifications require careful balancing. Too much variation and the entire structure of the cosmic microwave background would unravel. The observational side of this debate is equally intense. JWST's near-infrared detectors have pushed the observable frontier to redshifts above 13, meaning we can now see light emitted barely 300 million years after the Big Bang. Many of these sources were initially thought to be galaxies containing hundreds of millions of solar masses and stars. If correct, those values were catastrophic for ΛCDM, but subsequent analyses suggested that some of the brightness might come from intense bursts of star formation or from central black holes, rather than from fully developed stellar populations. The universe might not be as heavy as it looks, just more efficient at shining. Still, even after accounting for these corrections, the tension remains. Spectroscopic confirmation of several high redshift systems shows metallicities comparable to much later galaxies, meaning multiple generations of stars must have lived and died by that time. The chemical fingerprints do not lie. This implies that star formation began extraordinarily early, perhaps within 100 million years of the Big Bang, a timeline that leaves almost no room for delay. This realization forces cosmologists to revisit the initial conditions themselves. In the earliest moments, quantum fluctuations in the inflaton field seeded the density variations that would later grow into galaxies. The amplitude of those fluctuations, measured by the cosmic microwave background, sets the baseline for all later structure. But what if inflation produced more variance on small scales than we can detect in the CMB? Slightly stronger early perturbations could jumpstart the formation of massive halos. Some models of blue-tilted primordial power spectra explore exactly this possibility, suggesting that fine-scale enhancements in density may have acted as cosmic accelerants. Webb's contribution is to provide the data needed to test such subtle ideas. By counting the number and luminosity of galaxies at different redshifts, astronomers can reconstruct the growth rate of structure over time. The emerging picture is both exhilarating and uncomfortable. It suggests that either baryonic physics is far more efficient than simulations allow, or that the very scaffolding of the universe formed under different rules. Hydrodynamical simulations like Illustris, FIRE, and EAGLE have been recalibrated to include stronger feedback, more rapid cooling, and more turbulent accretion flows. Some runs now reproduce early, massive galaxies, but at the cost of fine-tuning parameters far beyond observational justification. When a model only works after one adjusts every dial to its extreme, scientists know they are brushing against the limits of comprehension. An alternative interpretation is philosophical as much as physical, that the universe is not uniform in its history. Certain regions might have evolved faster than others due to local variations in density, magnetic fields, or dark matter composition. In such a patchwork cosmos, the galaxies we observe at extreme redshifts might come from rare overdense zones, cosmic cities that developed earlier than the average. This would not violate ΛCDM globally, but would make our window into the past biased toward exceptional places. JWST's deep field observations, targeting gravitational lens clusters and narrow sightlines, could naturally select such extremes. Still, the possibility that new physics lurks beneath remains irresistible. The hints may come from the smallest scales, the internal structure of early galaxies. Many show dense, rotationally supported disks where theory predicts chaotic blobs. Others contain surprising bulges, suggesting rapid angular momentum transfer and early stabilization. Such features might require exotic mechanisms, perhaps magnetic turbulence or interactions between baryonic and dark matter through yet unknown forces. Some physicists even revisit modified gravity frameworks like MOND or emergent gravity theories, though these remain controversial. As Webb continues to gather spectra, another layer of complexity emerges: the cosmic web itself. The galaxies are not randomly scattered but lie along vast filaments of gas and dark matter, stretching hundreds of millions of light years. The pattern resembles neural networks or river deltas, channels through which matter flows toward nodes of higher density. These filaments existed astonishingly early. Some of Webb's deep fields already show protoclusters and filamentary alignments at redshifts above 10. If these structures are real, they imply that the large-scale geometry of the universe crystallized almost immediately after recombination. Understanding how this architecture arose requires merging physics across scales, from quantum fluctuations to galactic dynamics. The standard model of cosmology handles large scales beautifully, predicting the cosmic microwave background and baryon acoustic oscillations with exquisite precision. But it struggles to connect those grand averages with the messy, non-linear processes of star formation and feedback. Webb's data sit exactly at this interface. They reveal where the elegant mathematics of ΛCDM meets the chaotic creativity of nature. What makes this era scientifically thrilling is that every explanation carries risk. If the observations can be reconciled by refining models of star formation and feedback, then cosmology remains intact but gains complexity. If not, we may be approaching the end of ΛCDM as a complete theory. Some researchers already speak of a post-ΛCDM paradigm, one that incorporates dynamic dark energy, alternative inflation models, or new particle physics. The field is now in the same state as physics before quantum mechanics. The equations still work, but the anomalies are multiplying. The tension is not only mathematical, it is emotional. For nearly 3 decades, cosmology has enjoyed a sense of closure. The parameters were known, the model consistent, the universe understood in broad strokes. Webb's discoveries reopen the story. They remind scientists that comprehension is provisional, that the cosmos is not a solved puzzle, but a living experiment. The very success of ΛCDM may have lulled us into forgetting how wild reality can be. Beyond theory, the observational challenge grows. Measuring masses and ages of faint galaxies at extreme distances is difficult. Redshift estimation, contamination from active nuclei, and gravitational lensing distort signals. Some early, record-breaking galaxies turned out to be less massive once spectroscopic confirmation arrived. Yet others remained stubbornly large. Each correction refines, but does not erase the paradox. Even conservative estimates leave galaxies 2 or 3 times more massive than expected. The implications ripple outward. If structure formation began earlier, the timeline for chemical enrichment, planet formation, and possibly habitability also shifts. The ingredients for life, carbon, oxygen, nitrogen, could have appeared in the first billion years, far sooner than previously believed. That means the potential for ancient biospheres orbiting second-generation stars in primordial galaxies is no longer science fiction. It is a logical extension of chemistry. Webb's future spectroscopic surveys will search for molecules like carbon monoxide and water vapor in those ancient systems, probing the universality of life's precursors. Another subtle revelation lies in the color of the galaxies themselves. Many exhibit unexpectedly red spectral slopes, not from dust extinction but from stellar aging, implying populations of intermediate mass stars already several hundred million years old. That too compresses the cosmic timeline. If those stars existed, their progenitors must have formed almost immediately after recombination, when the universe was barely 1% of its current age. These facts push astronomers to rethink what they mean by early. Perhaps the universe had multiple starts, phases of accelerated structure formation triggered by feedback loops and local gravitational instabilities. The first galaxies might not represent the true beginning of cosmic order, but a resurgence after earlier, short-lived bursts. Such a scenario would preserve the spirit of ΛCDM, while admitting that evolution can proceed in pulses rather than in a single smooth ascent. Philosophically, the lesson is humility. Each generation of telescopes expands the horizon only to reveal deeper mysteries. The Webb telescope was designed to confirm theories. Instead, it has revived the art of questioning. The too big, too early paradox is not merely about galaxies. It is about our assumptions regarding time, causality, and emergence. Perhaps the universe is not constrained by our categories of early and late, simple and complex. Perhaps complexity is intrinsic, erupting wherever physics allows, as soon as energy and matter can communicate. In that light, the early universe is not primitive at all. It is a place where simplicity and sophistication coexist, where gravity, radiation, and quantum mechanics form a self-organizing system. The galaxies that Webb sees are not errors. They are reminders that the cosmos has always been capable of more. The challenge now is to adjust our understanding to match that capability without abandoning the rigor that makes science trustworthy. As Webb continues its mission, new instruments, Euclid, the Nancy Grace Roman Space Telescope, and the Vera Rubin Observatory, will join the effort, each attacking the problem from a different angle. Together, they will map dark matter through gravitational lensing, measure dark energy evolution, and trace galaxy formation across cosmic time. The future of cosmology will likely be written not in single revelations, but in the synthesis of vast, interlinked datasets. For now, one truth stands clear. The early universe refuses to behave like a beginner. It writes its story in mature handwriting, confident, structured, and defiant of simplification. JWST has merely opened the first page. What lies ahead will determine whether we refine our models or rewrite them entirely. In every direction Webb looks, light and gravity appear locked in a feedback cycle, a cosmic conversation between the visible and the invisible. The same energy that sculpts galaxies also threatens to unmake them. The early universe was not a calm arena of slow accumulation. It was a storm of interactions in which radiation, matter, and space-time continuously negotiated their boundaries. To understand why the first structures evolved so fast, one must examine not just what the universe contained, but how those contents talked to each other. When the first stars ignited, they transformed the darkness surrounding them. Their ultraviolet photons ionized the hydrogen that filled intergalactic space, tearing apart atoms and releasing electrons. The process, called reionization, changed the transparency of the cosmos. Before it began, light could not travel far. The universe was filled with a fog of neutral gas that absorbed every photon. After reionization, that fog lifted, and light could finally roam. This transition, occurring between roughly 200 and 800 million years after the Big Bang, is the threshold between cosmic infancy and cosmic adolescence. What Webb reveals is that this transition may have been driven not only by ordinary stars, but by multiple energy sources: supernova, black hole accretion, and perhaps even exotic particles decaying in the early dark matter halos. Each source contributed a different wavelength, and together they rewrote the thermodynamic balance of space. The radiation heated the intergalactic medium, changing the pressure gradients that guide gas toward forming galaxies. This created a self-regulating ecosystem. Star formation produced radiation, radiation altered gas flow, and gas flow controlled future star formation. Feedback is the term astronomers use for this loop, but the word understates its complexity. It is less a loop than a symphony of cause and effect extending across billions of light years. Supernova explosions were among the earliest conductors of this symphony. When massive stars ended their lives, they released heavy elements, carbon, oxygen, iron, into the surrounding gas. These metals allowed new clouds to cool faster by radiating heat, enabling the next generation of stars to form more efficiently. At the same time, the explosions blasted gas out of shallow gravitational wells, slowing formation in small galaxies. The result was a rhythmic pattern: creation, destruction, enrichment, pause, and renewal. In today's massive galaxies, this rhythm continues at a slower tempo, but in the first billion years it was furious, with entire systems cycling through generations in tens of millions of years. Black holes amplified this drama. When they fed, they released jets of relativistic plasma that could pierce through galaxies and deposit energy tens of thousands of light years away. Observations of distant quasars show that such outflows carry enough momentum to strip gas from their hosts, quenching star formation. Yet paradoxically, the same jets may have triggered star birth in neighboring regions by compressing gas clouds. Every photon and particle emitted by these ancient engines carried both creative and destructive potential. The cosmic feedback loop is not linear, it is dialectical, each process giving rise to its opposite. Recent hydrodynamic simulations now attempt to capture these interactions with increasing realism. Using tens of millions of CPU hours, researchers model how radiation pressure, magnetic fields, and turbulence cooperate or compete. The emerging picture is that of a finely tuned ecosystem, where small variations in initial density or feedback efficiency can decide whether a galaxy becomes a sprawling spiral or a quenched elliptical. Webb's high-resolution imaging allows these models to be tested directly by revealing the shapes of young galaxies at redshifts greater than 10. Some show smooth disks, others irregular clumps connected by luminous filaments, possible traces of feedback-driven winds colliding with inflowing gas. The timing of these feedback events may explain why the early cosmos matured so rapidly. If the first generations of stars were unusually massive, population 3 stars, their lifespans were short, but their influence immense. Each one could emit more ionizing radiation than 1 million suns, carving cavities in the primordial gas. When they exploded, they seeded their surroundings with metals that cooled subsequent clouds more effectively. In this scenario, the very first light accelerated the universe's own evolution by making it easier for the next wave of light to appear. Light, once born, taught the cosmos how to make more of itself. At larger scales, feedback shaped not just individual galaxies, but the geometry of the cosmic web. Ionized bubbles expanded and merged, linking regions that had previously been isolated. The boundaries between ionized and neutral zones acted like cosmic shock fronts, concentrating matter along their surfaces. In this way, radiation sculpted the skeleton of the universe, reinforcing the gravitational scaffolding set by dark matter. The result was a multi-layered architecture. Gravity drew the lines and light inked them in. Observations of the 21-centimeter hydrogen line promise to map this architecture in unprecedented detail. Instruments such as the Square Kilometre Array will measure tiny fluctuations in radio emission from the era of reionization, allowing scientists to see where and when the first luminous objects altered their surroundings. Combined with Webb's infrared vision, these data will reveal how feedback propagated through space, how one galaxy's radiation might have influenced another hundreds of thousands of light years away. The early universe was, in effect, a network of interactions rather than a collection of isolated islands. Within galaxies, feedback also governs the delicate balance between chaos and order. Without it, gas would collapse too quickly, forming stars until nothing remained to sustain future generations. With too much feedback, gas would be expelled entirely, halting formation. Somehow, nature found a middle path. The same gravitational potential that traps gas also traps the energy released by stellar winds and supernovae. recycling it into turbulence that supports new clouds. This self-organization is one of the most striking features of cosmic evolution. Systems far from equilibrium develop structures that preserve their ability to change. One of Webb's most surprising findings is that many early galaxies appear surprisingly compact, dense spheres only a few hundred parsecs across, glowing intensely in the infrared. Their high surface brightness suggests that feedback had already begun to regulate their growth, preventing uncontrolled collapse. In effect, they had achieved equilibrium much earlier than expected. These miniature furnaces were efficient, not chaotic. The universe seems to have learned stability almost immediately after learning light. The physics behind this efficiency is becoming clearer. Radiative feedback from young stars exerts pressure on surrounding dust, while cosmic rays generated by supernovae provide an additional cushion. Magnetic fields, once neglected in early simulations, weave through these processes, channeling outflows and guiding inflows along invisible highways. Each feedback mode operates on different timescales, from the seconds of a stellar flare to the millions of years of galactic winds, but their combined effect is a steady dialogue between micro and macrocosmos. Even time itself participates in the loop. In general relativity, energy and momentum curve space-time, altering the rate at which clocks tick. Thus, every burst of light subtly reshapes the geometry through which subsequent light will travel. Over cosmic distances, these cumulative distortions become measurable as gravitational lensing, the bending of light by mass. Feedback, therefore, is not confined to matter and energy. It extends to the fabric of time. The evolution of the cosmos is a feedback process written into space-time's own equations. At the theoretical frontier, physicists are exploring whether this interconnectedness might reveal deeper principles. Some quantum gravity frameworks propose that space-time itself emerges from entanglement, that geometry is the macroscopic echo of information exchange. If true, feedback is not merely an astrophysical mechanism, but a fundamental property of reality. Information influencing the conditions for more information. The universe could then be seen as a self-computing system, where every photon and particle participates in updating the cosmic code. This perspective resonates with the data. The patterns seen in the cosmic web resemble neural networks, where feedback loops strengthen certain connections while weakening others. Galaxies along dense filaments grow faster, much like neurons linked by reinforced synapses. The analogy is not metaphorical poetry, it is mathematics. Both systems evolve according to differential equations that maximize connectivity under constraints of energy and entropy. The same logic that shapes cognition may also shape the cosmos. Of course, such parallels must be treated cautiously. The danger of anthropomorphizing the universe is ever present. Yet recognizing feedback as a universal principle bridges disciplines, from plasma physics to quantum information theory. It allows scientists to see cosmic evolution not as a chain of isolated events, but as a continuum of interaction. Each epoch hands its energy to the next. Each structure becomes the seed of another. The evidence is written in light itself. Spectral lines captured by Webb carry the fingerprints of countless feedback cycles. The metallic enrichment of gas, the ionization of hydrogen, the shock heating from stellar winds. By decoding these signals, astronomers reconstruct the conversation between radiation and matter across eons. Every photon arriving at Webb's mirror has survived a gauntlet of feedback, absorbed, re-emitted, scattered, and redshifted, before completing its journey. In that sense, the telescope is not merely observing the universe, it is intercepting a message that the cosmos has been refining for 13 billion years. In the coming decade, multi-messenger astronomy will extend this dialogue beyond light. Gravitational wave detectors will capture the tremors of merging black holes, while neutrino observatories will sense the ghostly particles born in stellar explosions. Together, they will form a feedback map of energy transformation, linking events across the spectrum of forces. The goal is not just to collect data, but to understand how every form of energy exchange fits into the grand narrative of cosmic regulation. The cosmic feedback loop, then, is more than a process. It is the engine of cosmic evolution. Without it, galaxies would burn out quickly, structures would remain primitive, and the universe would lack the diversity we observe. With it, the cosmos becomes self-refining, adjusting its parameters as it evolves. Every explosion carries information forward. Every collapse sets the stage for the next emergence. From a human standpoint, studying this loop offers a kind of mirror. Civilization, too, evolves through feedback, knowledge leading to technology, technology altering perception, perception reshaping knowledge. In tracing how light, gravity, and time sculpted the cosmos, we trace the logic that also shapes our own understanding. The universe does not merely host observers, it generates the conditions under which observation becomes possible. The James Webb Space Telescope's early data introduced a tension that reverberated through cosmology. Images from its first deep fields revealed galaxies that appeared both massive and mature at a time when, according to standard models, the universe should have been barely capable of assembling such structures. These objects existed only a few 100 million years after the Big Bang, yet some contained as much stellar mass as the Milky Way. For decades, cosmological simulations had suggested that galaxies of that scale would take billions of years to form. Now the sky itself seemed to disagree. The discovery did not overturn physics, but it forced scientists to reconsider the sequence of cosmic growth. Perhaps the early universe was more efficient at converting gas into stars than anyone expected. Or perhaps the models were missing an ingredient, a process that accelerates structure formation without breaking the known laws of matter and gravity. In the language of science, it was not a contradiction. It was a puzzle with stakes that reached to the foundations of cosmology. The paradox, often called too big, too early, originates from how astronomers translate faint light into physical properties. Webb's infrared detectors capture photons that have traveled for more than 13 billion years, stretched by the expansion of space into long wavelengths. From those spectra, researchers estimate the redshift, which corresponds to distance and cosmic age. They also estimate mass and star formation rates by fitting the spectral energy distribution, the balance of light across different wavelengths, to population models of stellar evolution. The surprising part was not the brightness itself, but how much mass seemed required to produce it. At redshifts greater than 10, corresponding to a universe younger than 500 million years, Webb detected sources whose luminosities implied stellar populations of more than 10 billion solar masses. If those estimates were correct, it would mean that stars had formed in furious bursts, converting gas into light with an efficiency far higher than modern galaxies achieve. The question, then, was whether the light truly belonged to stars at all. Some astronomers suggested that active black holes, glowing in the ultraviolet and X-ray bands, might account for part of the brightness. Others proposed that the stellar populations might be metal-free, composed of the very first stars, which burn hotter and brighter than any that exist today. To resolve these possibilities, scientists turned to spectroscopy. Each chemical element leaves a signature in the light it emits or absorbs. If the galaxies were dominated by massive metal-poor stars, their spectra would lack the fingerprints of heavy elements like oxygen or iron. Conversely, if supermassive black holes powered the glow, the spectra would reveal high ionization lines characteristic of accretion disks. Webb's instruments, particularly the NIR spec and MIRI spectrographs, began collecting data capable of distinguishing between these scenarios. The results so far hint at a mixed picture. Some early galaxies do indeed contain surprisingly evolved chemical compositions, while others appear almost pristine, as if only recently formed from primordial gas. This diversity complicates any single explanation. In theoretical simulations, the growth of galaxies depends on a balance between gravity, gas cooling, and feedback from radiation and supernovae. Increase one parameter too much, and galaxies overproduce stars. Decrease it, and the cosmic web remains dim and empty. The early JWST observations suggest that nature may have tuned these parameters differently during its youth. Perhaps dark matter halos, the invisible gravitational wells that host galaxies, collapsed earlier than predicted. Or perhaps the baryonic matter within them cooled more efficiently, fragmenting into dense clumps that ignited star formation rapidly. Some researchers have revisited the possibility that dark matter itself might not be entirely cold. In the standard ЛCDM model, Dark matter consists of slow-moving, collisionless particles that form hierarchical structures from small to large scales. But if dark matter were slightly warm, composed of lighter particles moving at relativistic speeds, the pattern of collapse could shift. Small structures might form earlier or dissipate differently, changing the timeline of galaxy assembly. Other theories invoke dark energy's early influence, suggesting that the accelerating expansion may not have been uniform through time. A small variation in its density could have altered how matter clumped together during the first billion years. Even the initial conditions of the universe are being re-examined. The inflationary epoch, a burst of exponential expansion immediately after the Big Bang, left subtle imprints in the density fluctuations that seeded galaxies. If inflation produced slightly stronger or asymmetric perturbations at certain scales, those regions could have formed stars sooner. JWST's observations provide, for the first time, direct constraints on those primordial imprints. In effect, every unexpectedly massive galaxy becomes a data point about the physics of the Big Bang itself. The implications reach beyond cosmology. If large galaxies already existed 500 million years after the beginning, then the environments capable of hosting complex chemistry, and perhaps even prebiotic molecules, also existed earlier than assumed. The cosmic clock of habitability might have started ticking sooner. While no one claims life emerged at such epochs, the presence of stable, metal-enriched systems suggests that the universe began preparing its chemistry almost immediately after it learned to shine. NASA's teams emphasize caution. The early JWST results are based on relatively small samples, often at the edge of the telescope's sensitivity. Photometric redshifts, estimates derived from brightness rather than detailed spectra, carry uncertainties that can shift objects by hundreds of millions of years in age. As more spectroscopic data accumulate, some galaxies once thought to be ancient have been reassigned to later epochs. Yet even after accounting for these corrections, the overall message remains the same. The early universe was astonishingly productive. Simulations such as Illustrious TNG, Eagle, and Fire are now being recalibrated to test whether plausible changes in feedback or gas dynamics can reproduce Webb's findings. Preliminary results show that if star formation efficiency increases modestly with gas density, as expected in turbulent, metal-poor environments, massive galaxies can appear sooner without violating fundamental physics. This suggests that the cosmos may simply be more flexible than our models allowed, capable of finding pathways to complexity faster than anticipated. At the same time, Webb's images reveal galaxies with irregular, clumpy morphologies, hints of mergers in progress. Collisions between small proto-galaxies could accelerate growth by funneling gas into central regions where stars form in bursts. Such interactions also feed black holes, which in turn release energy that regulates further formation. The result is a feedback loop on a cosmic scale. Gravity builds structures, feedback sculpts them, and the dance repeats. As the telescope continues its survey, astronomers are expanding their search beyond brightness alone. Gravitational lensing, the bending of light by massive foreground clusters, magnifies faint background galaxies, allowing Webb to probe even earlier epochs. These natural cosmic lenses act as time machines, revealing galaxies at redshifts above 12, when the universe was less than 400 million years old. Some of these lensed systems appear tiny, but are packed with stars at densities that challenge existing theories of stability. Whether these early giants represent the norm or the exception is still unknown. Future observations, including spectroscopic campaigns with Webb's NIR-CAM GRISM and complementary data from upcoming telescopes like the Roman Space Telescope and the ground-based Extremely Large Telescope, will refine the picture. Each new dataset narrows the margin of uncertainty, turning speculation into a measurable constraint. What began as a shock is becoming an opportunity, a chance to rewrite the timeline of creation with higher precision. The early galaxies do not overthrow the standard model. They enrich it. They remind scientists that cosmology, for all its equations, remains an empirical science, bound to the evidence written in light. The universe is not misbehaving. It is revealing more of its complexity. The deeper we look, the more we see that cosmic evolution is not a straight line, but a branching tree, full of shortcuts that matter and energy discovered long before we did. Among the most unexpected implications of Webb's early findings is the revival of an idea once considered purely speculative, the concept of dark stars. These hypothetical objects, first proposed in theoretical astrophysics almost 2 decades ago, might represent a transitional stage between the primordial gas clouds of the early universe and the first true stars. Unlike normal stars that ignite through the nuclear fusion of hydrogen, dark stars would shine through the annihilation of dark matter particles within their cores. Webb's observations of extremely bright objects at redshifts above 10 have brought this idea back into serious discussion. In standard cosmology, dark matter is invisible, interacting only through gravity and possibly the weak nuclear force. Yet if dark matter consists of self-annihilating particles, such as weakly interacting massive particles known as WIMPs, then wherever their density becomes high, the collisions could produce a continuous flow of energy. In the dense centers of the earliest halos, this energy might have been sufficient to halt gravitational collapse temporarily, creating large, diffuse objects powered by dark matter heating rather than fusion. A dark star would not be dark at all. Its surface could radiate intensely in infrared light, its luminosity comparable to or exceeding that of fusion-powered stars. But its temperature would be cooler, its structure puffed up to enormous scales, possibly tens of astronomical units across. Because of that size, a single dark star could mimic the brightness of an entire small galaxy when seen from billions of light-years away. When Webb detected several compact but extremely luminous sources at redshifts above 13, some researchers suggested that at least a few of them might be dark stars rather than galaxies. If such objects truly existed, they would alter the story of cosmic dawn. They could persist for millions, or even hundreds of millions of years, delaying the onset of fusion in their cores until the dark matter fuel was exhausted. When the annihilation ceased, the gas would collapse further, igniting conventional nuclear reactions and possibly forming the first generation of supermassive stars. These, in turn, might have left behind the seed black holes that later grew into the quasars we observe at high redshift. Thus, dark stars could provide a natural pathway between the microphysics of dark matter and the macroscopic structure of galaxies. The idea remains controversial. Webb's data are exquisite but not yet decisive. Distinguishing a dark star from a compact galaxy requires detailed spectral fingerprints. A galaxy's spectrum reveals multiple stellar populations and chemical enrichment, while a single dark star would exhibit a smooth continuum with characteristic absorption edges determined by its surface temperature. Preliminary analyses of the brightest early sources show mixed signs. Some appear consistent with star-forming galaxies, others with the more exotic possibility of dark matter heating. Upcoming longer integrations will push the sensitivity of Webb's NIR-SPEC and MIRI instruments to the limits of detection, seeking traces of molecular hydrogen or absence of metallic lines that could confirm or rule out the hypothesis. Even if no dark stars are ultimately found, the theoretical exercise has already deepened the understanding of how energy flows in the early cosmos. It forces astrophysicists to test the boundary between gravitational and particle physics. The same annihilation mechanism invoked for dark stars also affects the thermal history of the intergalactic medium. If dark matter interactions deposited significant heat into primordial gas, the timing of ionization and the pattern of 21-centimeter emission would change. Future radio observations by the Square Kilometre Array may detect or constrain such effects, turning the dark star debate into a measurable parameter of cosmology. Meanwhile, Webb continues to map a universe more intricate than theory predicted. Its spectroscopic surveys reveal chemical diversity across even the earliest galaxies. Some systems contain heavy elements that must have been forged in prior generations of supernovae, implying rapid recycling of material. Others remain pristine, dominated by hydrogen and helium. This patchiness suggests that star formation and enrichment proceeded unevenly, with localized bursts separated by long, quiet periods. Dark matter heating, stellar feedback, and mergers all contributed to this mosaic, weaving complexity far earlier than models expected. Parallel to these observations, theorists are refining models of how the first black holes emerged. One persistent puzzle is the existence of quasars less than 1 billion years after the Big Bang, whose central black holes weigh more than 1 billion suns. Traditional growth by accretion from stellar remnants cannot explain such rapid accumulation. One proposed solution is direct collapse, the formation of massive black holes from gas clouds that never fragment into stars. Another, more speculative, is that dark stars themselves collapse directly into black holes of thousands of solar masses once their dark matter heating ceased. In that view, the early universe's most luminous quasars could be the fossils of dark star evolution. Every new observation from Webb helps discriminate among these pathways. The telescope's deep field images capture not only galaxies, but the faint halos of diffuse light surrounding them, revealing how energy escapes and interacts with the intergalactic medium. Polarization measurements and spectral gradients allow astronomers to trace outflows, winds, and ionization fronts. Step by step, a more physical picture replaces the earlier statistical one. The universe's first billion years are no longer an abstract epoch inferred from models. They are becoming a directly observable landscape. What makes this progress remarkable is how it connects the smallest scales to the largest. The behavior of hypothetical dark matter particles, their mass, interaction cross-section, and annihilation rate, influences the architecture of galaxies hundreds of thousands of light-years across. The luminous fog Webb detects is the visible shadow of invisible physics. Whether or not dark stars prove real, the search for them exemplifies the new era of astronomy, a union of particle physics, astrophysics, and cosmology, where telescopes act as laboratories for fundamental forces. In that sense, Webb is not merely looking back in time, but across disciplines. Its mirror collects photons that carry clues about the universe's structure, composition, and even its unseen ingredients. Each spectrum is an experiment, each anomaly a potential revision of how reality organizes itself. As datasets expand, the debate will sharpen. Are these bright primordial sources clusters of ordinary stars, or windows into a darker kind of physics? The answer will determine not only the history of the first light, but the future direction of cosmology itself. The next decade will decide the matter. Coordinated campaigns combining Webb with the upcoming Roman telescope and the Vera C. Rubin Observatory will provide complementary perspectives: infrared precision from space, optical depth from the ground, and gravitational microlensing to weigh unseen structures. If dark stars exist, their population statistics should emerge naturally from such surveys. If they do not, the constraints will still refine dark matter models and early galaxy formation theories with unprecedented rigor. Either outcome represents progress. For now, the cosmos keeps its secret in the faint red shimmer of light older than the Earth itself. Somewhere in that glow may lie the trace of the first engines that taught the universe how to shine, not through fusion, but through the slow, silent burn of matter's invisible twin. The galaxies that Webb sees in the ancient darkness are not isolated anomalies. They are the ancestors of everything that now fills the cosmic web, the vast filamentary network of matter that stretches across the observable universe. Understanding how those first dense knots of light evolved into the spirals and ellipticals of the modern era requires tracing the transformation of matter across more than 13 billion years. What began as fluctuations in quantum fields became galaxies, clusters, and voids, a process guided by gravity but choreographed by feedback, radiation, and cosmic expansion. Every galaxy that Webb captures at extreme redshift sits within a larger architecture shaped by invisible scaffolding. Dark matter forms the framework of that architecture. Its filaments thread through the universe like the grain of wood, defining where baryonic matter, the ordinary atoms that make stars and planets, can accumulate. As gas falls into these gravitational troughs, it compresses and cools, igniting bursts of star formation. The earliest galaxies grew at the intersections of these filaments, where flows of gas converged from multiple directions. Simulations now show that such intersections, known as nodes, acted like cosmic cities, dense regions of matter attracting more matter, forming the seeds of the massive clusters that dominate the present-day universe. But this growth was anything but peaceful. The first galaxies existed in a dynamic balance between inflow and outflow, a competition between gravity pulling gas inward and radiation driving it outward. The early universe, therefore, was not a place of quiet accumulation, but of constant exchange, a turbulent ecology of energy. At the heart of this process lies the question of efficiency. How did these systems convert gas into stars so rapidly? Observations suggest that early galaxies operated under extreme conditions: high gas density, intense ultraviolet radiation, and strong magnetic turbulence. These factors compressed star-forming clouds beyond the thresholds seen in local galaxies. Yet feedback prevented runaway collapse. Supernova explosions, stellar winds, and radiation pressure acted as safety valves, dispersing gas just enough to allow new structures to form without exhausting the reservoir entirely. Webb's high-resolution images reveal evidence of this dynamic in the morphology of early galaxies. Many appear clumpy or asymmetric, with bright cores surrounded by diffuse halos. These patterns indicate ongoing mergers and tidal interactions. When small galaxies collide, their gas clouds compress, triggering starbursts. At the same time, gravitational forces distort their shapes, feeding central black holes and producing energetic outflows. This interplay of collision and feedback accelerates both growth and regulation, a self-balancing act written into the universe's design. As these systems matured, they began assembling into larger associations. Groups of a few galaxies merged into clusters of dozens or hundreds, bound together by the deep gravity wells of their combined dark matter halos. Within these clusters, interactions became frequent. Galaxies exchanged gas through tidal stripping, and shock waves from collisions heated the intracluster medium to millions of degrees. This hot plasma emits X-rays detectable even today, a lingering signature of ancient violence. The transition from the early chaotic epoch to the structured universe we see now marks a profound shift in cosmic behavior. In the beginning, everything changed rapidly. Gravitational collapse occurred faster than cooling or feedback could stabilize it. Over billions of years, as density decreased and expansion slowed interactions, cosmic evolution entered a gentler rhythm. Large galaxies began forming stable disks, their star formation rates declining to sustainable levels. The cosmic star formation rate peaked roughly 10 billion years ago and has been falling ever since. This decline does not signal decay, but maturity. The universe has entered a phase of equilibrium, where the energy generated by stars, supernovae, and active nuclei balances the inflow of new material. Yet the legacy of those first billion years remains embedded in every structure we observe. The metallicity gradients in galactic disks, the distribution of stellar ages, and even the chemical composition of planetary systems all carry the imprint of those early feedback cycles. Cosmic structure formation also reveals the deep connection between the visible and the invisible. The clustering of galaxies mirrors the clustering of dark matter, but not perfectly. On small scales, baryonic physics modifies the pattern. Feedback-driven outflows redistribute gas, smoothing out some of the sharp features in the dark matter distribution. This baryonic back reaction is now one of the key uncertainties in cosmology. Webb's observations help quantify it by showing how gas and stars trace, or fail to trace, their underlying halos at different epochs. Meanwhile, gravitational lensing provides a direct probe of the dark scaffolding itself. When light from distant galaxies passes near massive clusters, its path bends, magnifying and distorting the image. By analyzing these distortions, astronomers can reconstruct the mass distribution along the line of sight, mapping dark matter with unprecedented precision. In combination with Webb's infrared imaging, lensing studies are beginning to reveal how the invisible skeleton evolved, how filaments thickened, nodes merged, and voids expanded. These maps show a universe that is both orderly and restless. Large-scale structures appear stable, yet within them, motion never ceases. Gas continues to fall along filaments into galaxy clusters. Star formation persists in dense pockets, even as others fade. Black holes still feed, driving outflows that shape their surroundings. The same feedback processes that governed the first galaxies remain at work today, only on larger scales and slower tempos. Cosmic evolution, it seems, is a fractal process, the same patterns repeating across time and magnitude. Recent advances in computational astrophysics allow researchers to rewind this cosmic film in reverse. By matching simulations to observations, they can trace present-day galaxies back to their proto-galactic ancestors. The Milky Way, for example, appears to have originated from a network of small halos that merged around 13 billion years ago. Webb's deep fields may have already imaged analogs of those building blocks, giving us a glimpse of our own cosmic infancy. The feedback principles discovered in early epochs also illuminate how galaxies like ours maintain long-term balance. In the Milky Way, supernovae heat the interstellar medium, creating bubbles of hot gas that rise into the halo before cooling and raining back down, a galactic fountain that recycles material over hundreds of millions of years. Similar cycles likely operated in the first galaxies, but on shorter timescales. Understanding those ancient rhythms allows scientists to connect the microphysics of star formation to the macrophysics of cosmic structure. Yet, one mystery persists. Observations show that only a small fraction of baryonic matter, less than 10%, resides in stars and galaxies. The rest remains in diffuse gas spread throughout the cosmic web. This missing baryon problem has puzzled astronomers for decades. Webb's spectroscopy, combined with X-ray and radio data, is beginning to locate this hidden matter in the filaments that connect clusters. These faint structures, glowing weakly in the infrared, represent the arteries of the cosmic network through which matter and energy continue to flow. In this context, the early massive galaxies that once seemed anomalous now appear as the first hubs of a grander system. They were not mistakes in the cosmic record, but the pioneers of structure, the first nodes of a network that would span the cosmos. Their rapid growth, once seen as a contradiction, may have been a necessary step in creating the complexity we observe today. The universe, from the start, was predisposed toward connection, gravity linking matter, radiation linking time, and feedback linking cause with consequence. Ultimately, Webb's revelations invite a shift in how we think about cosmic history. The question is no longer simply when galaxies formed, but how the universe organizes itself into self-sustaining hierarchies. Each level, from particle interactions to galactic superclusters, operates under the same principle of feedback and equilibrium. The laws of physics do not merely describe motion, they encode the capacity for adaptation. The cosmos behaves less like a static machine and more like an evolving organism, continuously refining its structure through the exchange of energy and information. In this view, the first galaxies were not endpoints but beginnings of a recursive process that continues to the present day. Their light, now arriving at Webb's mirror after billions of years, is both a message and a mirror. It tells us that complexity emerges wherever feedback and gravity coexist, and it reflects the same logic that governs our own evolution, an unfolding symmetry between knowledge and the universe that produces it. As Webb continues its observations, the image of the early universe becomes not simpler but richer. Every field the telescope studies reveals new structures, faint filaments of light that stretch farther than expected, galaxies merging into forms that defy linear description. The cosmic web is not a static lattice frozen in time. It is a living topology of flows. Matter does not simply fall into potential wells. It circulates, evaporates, condenses, and migrates across scales. The distinction between galaxy, cluster, and void grows less clear as scientists begin to realize that these categories are phases of the same continuous medium. When astronomers model these environments, they now describe them in the language of fluid dynamics rather than solid geometry. The intergalactic medium behaves like a turbulent ocean of plasma, threaded with magnetic fields and stirred by supernova winds. Filaments of warm, hot gas connect galaxies like rivers between lakes, carrying the chemical products of stellar evolution across millions of light years. In this sense, the universe is self-pollinating. Heavy elements forged in the hearts of early stars drift outward, enriching regions that have never known starlight. The cosmos, by its very nature, distributes what it learns. The mechanisms of this distribution depend on both violence and balance. Shock waves from supernovae propagate through halos, heating surrounding gas and setting off ripples of compression that seed future star formation. Active galactic nuclei inject vast amounts of kinetic energy into the intracluster medium, sculpting cavities and jets that can stretch for hundreds of thousands of light years. These structures, once viewed merely as destructive, now appear as stabilizing influences. By preventing the runaway cooling of gas, they keep galaxies from collapsing into sterile cores. In thermodynamic terms, feedback increases entropy locally but preserves structure globally, a paradox at the heart of cosmic order. As Webb peers deeper, the distinction between local and cosmic begins to dissolve. A single supernova observed at high redshift becomes a sample of universal behavior. Its light curve and spectral features encapsulate the same physics that governs entire galaxies. The repetition of patterns across magnitude scales suggests that the universe is self-similar, a concept supported by both mathematical models and observation. Fractality in the large-scale distribution of matter, intermittency in star formation rates, and scaling laws between black hole mass and galactic bulge all hint at an underlying symmetry that transcends specific epochs. The search for that symmetry drives modern cosmology. Gravity alone cannot account for it, nor can baryonic processes fully explain the coherence of structures spread across billions of light years. Researchers are turning toward frameworks that treat information itself as a physical quantity. In these models, entropy, feedback, and structure emerge naturally from the dynamics of information exchange. Space-time becomes an emergent geometry of relationships, not a stage upon which events unfold. Every photon Webb detects is thus an information transfer, a record of interactions encoded in frequency and phase. The universe, interpreted this way, is not merely expanding, it is computing. This computational view finds support in the data. When scientists analyze the cosmic microwave background, they see not randomness, but correlation, a memory of initial fluctuations stretched across the sky. Those patterns form the foundation upon which later structures grew. Webb's contribution is to show how those seeds matured, how information condensed into stars, galaxies, and ultimately the chemical complexity required for life. The chain is continuous. Quantum uncertainty gave rise to density contrast. Contrast produced gravity wells. Gravity produced energy gradients. And those gradients, through countless feedback loops, generated the diversity visible today. The observation of galaxies at redshifts beyond 12 marks not the end of discovery, but its beginning. Each detection pushes the boundary between known and speculative physics. To explain them, researchers are reconsidering the role of cosmic variance, the statistical unevenness inherent in finite observations. Some regions of the early universe may simply have evolved faster due to slightly higher initial densities. Others might host exotic conditions, such as variations in the local dark energy field or asymmetries in the neutrino background. What Webb offers is not a single narrative, but an atlas of possibilities, each patch of sky a different chapter in the same cosmic autobiography. The complexity of interpreting these signals forces collaborations between fields once considered separate. Particle physicists consult with astronomers to constrain dark matter candidates. Plasma physicists model the intergalactic medium using magnetohydrodynamics. Computer scientists develop machine learning algorithms to extract weak spectral signatures buried in noise. The telescope has become a meeting point for disciplines, its data serving as a common language through which different branches of science converse. In a subtle way, the structure of human knowledge mirrors the structure of the cosmos, decentralized, interconnected, and evolving through feedback. Even the concept of time, long treated as linear, begins to appear elastic when examined through Webb's lens. Photons from distant galaxies arrive stretched by cosmic expansion, carrying with them a record of how time itself has flowed. Observers on Earth are not looking back in time so much as looking across it, intersecting the light cones of events that coexist in space-time though separated by billions of years. In the equations of general relativity, these intervals are symmetric. The past of one observer can be the present of another, depending on perspective. The telescope, therefore, is not a time machine in the cinematic sense, but an instrument of simultaneity, revealing the coexistence of all epochs within the fabric of space. To study the early universe is to encounter the limits of language. Concepts like before and after lose precision when applied to a space-time that curves under its own weight. The photons Webb captures were emitted by sources that may no longer exist, yet their information persists, as if the universe refuses to forget. This persistence gives cosmology a philosophical weight. It demonstrates that nothing truly vanishes from the cosmic ledger. Energy transforms, matter decays, but information, the pattern of relationships, endures. That persistence becomes literal in the data. Webb's detectors record not single events, but cumulative histories. Each pixel in an infrared image represents millions of overlapping photons, their paths shaped by gravity, their energies modified by redshift, their origins blurred by cosmic dust. Deconvolving those signals requires both computational power and intuition. Scientists must decide which models to apply, which priors to assume, which uncertainties to tolerate. In doing so, they engage in a dialogue with the universe, refining their understanding through iteration. Knowledge itself becomes a feedback process, a microcosm of the cosmic one. Within this dialogue, surprises continue to emerge. Recent analyses have identified potential protoclusters at redshifts around 7 to 8, regions already showing the gravitational coherence expected of much later epochs. These structures suggest that the transition from isolated galaxies to networked clusters occurred swiftly, perhaps driven by synchronized star formation bursts across vast regions. The mechanism of that synchronization remains unknown. It may involve cosmic magnetism, radiation backgrounds, or collective oscillations in the density field. Whatever the cause, the effect is unmistakable. The universe evolved with remarkable coordination, as if responding to an unseen rhythm. The idea of rhythm recurs throughout astrophysics, from the periodic pulses of neutron stars to the oscillations of baryon acoustic waves. The cosmos reveals itself through repetition. Webb's instruments detect these patterns as subtle modulations in brightness and spectrum, signatures of cycles that link micro and macro scales. The same mathematics that describes atomic transitions governs galactic rotation curves. The same equations of fluid flow apply to the movement of gas clouds and the dynamics of entire clusters. Unity underlies diversity. The deeper one looks, the more the distinctions dissolve into correspondence. At this level of precision, cosmology becomes an exercise in humility. The telescope's discoveries continually remind scientists that every answer unfolds into new questions. Why do some galaxies form massive black holes while others remain quiescent? Why does dark energy behave like a constant rather than a variable field? Why do fundamental constants themselves appear finely tuned for the emergence of structure? These questions extend beyond empirical observation into the realm of principle. Webb cannot answer them directly, but it sharpens their contours, turning speculation into calculable hypotheses. In parallel, other observatories extend the reach of perception. The Laser Interferometer Space Antenna will soon open the gravitational wave window on the same epochs Webb sees in light. The square-kilometer array will trace the neutral hydrogen that filled the space between the first galaxies. Combined, these instruments will yield a multi-messenger portrait of cosmic evolution, light, gravity, and particles interwoven into one narrative. Each messenger tells part of the story. Only together do they reveal the full symphony. The more that story unfolds, the clearer it becomes that the early universe was not primitive, but sophisticated from its inception. Complexity did not emerge gradually. It was present in potential from the first moments of expansion. Webb's findings suggest that the laws of physics encode not just stability but creativity. Given the simplest ingredients, hydrogen, helium, gravity, and time, the universe constructs intricacy spontaneously. It builds systems capable of reflecting upon themselves. In this sense, observation is not an accident of evolution, but an inevitable outcome of the same principles that form stars and galaxies. This realization changes the tone of inquiry. Cosmology is no longer only about what happened, but about why such a narrative exists at all. The feedback mechanisms that regulate galaxies may also regulate knowledge itself. Observation alters models. Models alter perception. Perception guides further observation. The act of looking into the cosmos becomes part of the cosmos's own evolution, an extension of the same recursive logic that shapes everything from atoms to superclusters. Webb, floating at the L2 point far from Earth's noise, embodies that logic. A mirror catching light that has traveled for eons, returning it as understanding. The light continues to arrive, unending and inexhaustible. Each new dataset refines the cosmic map. Each correction deepens the mystery rather than resolves it. The early galaxies, the dark stars, the filaments, and the voids all form verses in a single poem written in photons. And still, beyond the farthest redshift Webb can reach, lies the unobserved, the realm where the first fluctuations began to stir, where time and space were indistinguishable, where potential awaited expression. The telescope edges closer, image by image, to that frontier, not to find an end, but to trace the continuity that binds all beginnings. For decades, astronomers have known that something fundamental was missing from the cosmic inventory. When they counted all the atoms predicted to exist based on measurements of the cosmic microwave background and primordial nucleosynthesis, only about half of that baryonic matter could actually be found in stars, gas clouds, and galaxies. The rest had vanished into invisibility, not because it did not exist, but because it had become too diffuse, too hot, or too faint to detect. This invisible reservoir, sometimes called the missing baryons, represents the hidden oceans of the universe, an intergalactic medium stretching between galaxies, threaded along the filaments of the cosmic web. Modern cosmology suggests that only about 5% of the total mass energy of the cosmos consists of baryonic matter, the ordinary particles that make up protons, neutrons, and atoms. Yet even within that small percentage, roughly half remains unaccounted for by traditional observation. Early missions such as COBE, WMAP, and Planck mapped the early universe with exquisite precision, determining how much normal matter should exist. The challenge shifted from prediction to detection. If the baryons were real, where did they go? The answer, now emerging through instruments like JWST, Chandra, and the XMM Newton X-ray Observatory, is that most of them are hiding in intergalactic space, heated by shock waves generated during the formation of cosmic structure. When galaxies and clusters condensed under gravity, the gas between them was drawn into filaments, compressed, and heated to millions of degrees. This process created what astrophysicists call the warm-hot intergalactic medium, or WIM. It is composed primarily of ionized hydrogen and helium, laced with trace elements such as oxygen, neon, and carbon, metals forged in the first generations of stars and dispersed by supernova explosions. The WIM is nearly invisible in visible light, but glows faintly in X-rays and ultraviolet, detectable only through its subtle absorption signatures against the bright light of distant quasars. To find it, scientists look for slight dips in a quasar's spectrum, fingerprints of highly ionized oxygen known as O-VIX and O-7. These features reveal gas at temperatures between 105 and 107 Kelvin, hot enough to strip electrons from atoms but not hot enough to emit strong X-rays on its own. Over the past decade, multiple observations have converged on this idea. The Chandra X-ray Observatory detected filaments of diffuse oxygen emission connecting clusters of galaxies such as Abell 222 and Abell 223. More recently, ESA's XMM Newton confirmed similar structures with improved resolution. These filaments appear to trace the scaffolding predicted by cosmological simulations, vast tendrils of gas stretching tens of millions of light-years, linking massive nodes where clusters reside. The cosmic web is not merely a metaphor. It is a physical network of baryons and dark matter, with the WIM acting as the connective tissue of the universe. The James Webb Space Telescope contributes to this investigation not by detecting the hot gas directly, but by identifying the galaxies and protoclusters that shape it. Webb's infrared sensitivity allows astronomers to trace star formation histories, metal enrichment, and outflows that seed the intergalactic medium. Each galaxy acts as both a source and a sink of baryons. It expels matter through supernova winds and active galactic nuclei, then reaccretes material along cosmic filaments. In this exchange, the missing baryons do not vanish. They circulate. The universe behaves less like a static archive of matter and more like a planetary ocean, with continuous currents of gas exchanging energy and momentum. Computer simulations such as Illustrious TNG and Eagle visualize these processes in remarkable detail. They show that nearly 30–40% of all baryons at the present epoch reside in the WIM phase, another 10% in the intracluster medium, and only a small fraction in stars or cold gas. The remainder drifts in cooler intergalactic clouds that feed galaxies from below the detection threshold of most telescopes. The models also reveal that feedback from black holes and supernovae plays a crucial role in maintaining the WIM's temperature. Without such energy input, the filaments would cool and collapse, erasing the delicate network that connects the cosmos. Energy transfer, therefore, becomes a structural necessity. The cosmic web is held together not only by gravity, but by heat. Detecting this web in emission remains one of modern astronomy's greatest technical challenges. The X-ray surface brightness of the WIM is thousands of times fainter than the background glow of our own galaxy. Instruments must be cooled to cryogenic temperatures and shielded from stray light to capture even a handful of photons per hour. Future missions such as ESA's Athena, Advanced Telescope for High-Energy Astrophysics, and NASA's proposed Lynx X-ray Observatory aim to map these faint filaments directly, transforming the missing baryons from inference to image. In parallel, radio observatories like the Square Kilometre Array will trace neutral hydrogen through its 21-centimeter line, filling in the colder portions of the cosmic ocean. The search for missing baryons is more than an accounting problem. It tests our understanding of how matter cycles through cosmic environments. Stars form from collapsing clouds, shine, die, and return material to the intergalactic medium. Over billions of years, this recycling sculpts the chemical composition of the universe. Elements like carbon and oxygen, the basis of life, spend most of their existence not in planets or stars, but adrift in intergalactic space. The atoms in a human body were likely dispersed through the WIM long before the Milky Way existed. The hidden oceans of baryons are, in that sense, ancestral seas from which all later complexity emerged. Beyond the chemical story lies a thermodynamic one. The WIM serves as a vast energy reservoir, storing heat generated by gravitational collapse. Shockwaves from infalling gas convert potential energy into thermal energy, while radiative cooling slowly releases it back into space. This interplay regulates star formation across the universe. When gas becomes too hot, it resists collapse, halting the birth of new stars. When it cools, it condenses and reignites the cycle. Observations suggest that this self-regulating feedback maintains a delicate equilibrium, preventing both runaway formation and permanent quiescence. The universe behaves like a thermostat, its temperature profile emerging naturally from the physics of feedback. A striking demonstration of this principle comes from recent observations of the Perseus cluster. High-resolution X-ray data reveal ripples in the intracluster medium, generated by the outbursts of a central supermassive black hole. These sound waves, each spanning hundreds of thousands of light years, transport energy outward and prevent the surrounding gas from cooling too quickly. On cosmological scales, similar processes may occur along filaments, with multiple galaxies collectively maintaining the thermal balance of their shared environment. Energy, like matter, flows through the cosmic web. The presence of these hidden baryons also refines measurements of cosmic expansion. Baryon acoustic oscillations, the faint imprints of pressure waves from the early universe, depend on the total amount of normal matter. By locating the missing baryons, astronomers can calibrate these standard rulers with greater precision, reducing uncertainties in the Hubble constant and dark energy models. In this way, the WIM is not merely a curiosity, it is an essential piece of the cosmological puzzle, linking small-scale astrophysics to the fate of the universe itself. Detecting the WIM has required not only better instruments, but also better statistical methods. Cross-correlation between X-ray, ultraviolet, and Sunyaev-Zeldovich (SZ) data has proven effective. The SZ effect, where hot electrons distort the cosmic microwave background through inverse Compton scattering, provides an independent measure of the hot gas pressure. When these distortions are aligned with known large-scale structures, they reveal the presence of diffuse plasma that optical telescopes cannot see. In 2020, researchers using the Planck satellite combined SZ maps with galaxy surveys to trace filaments between clusters, confirming that they contain a substantial fraction of the missing baryons. Each detection narrows the gap between theoretical expectation and observational reality. James Webb's role in this grand effort is increasingly synergistic. By identifying galaxies at the cosmic dawn with unexpectedly high metallicity, Webb shows that enrichment processes began far earlier than thought. The heavy elements observed in those systems could only have reached intergalactic space through powerful winds and outflows, early precursors of the WIM. In that sense, the telescope is witnessing the first stirrings of the hidden ocean, when newborn galaxies began to pollute and heat the space around them. The metals seen in the spectra of ancient quasars are the fossils of those tides. If current models are correct, the WIM accounts for most of the missing mass at low redshift, yet a fraction may remain in even fainter phases. Some gas may exist in a transitional state between warm and hot, detectable only through future ultraviolet spectroscopy from space. Proposed missions like LUVOIR and HABEX plan to target these elusive components, combining large mirrors with ultra-stable spectrographs capable of resolving individual absorption lines against the light of distant galaxies. Each new observation adds depth to the portrait of the cosmic ocean, turning what was once theoretical into empirical structure. The implications reach beyond cosmology. Understanding how baryons circulate through the cosmic web informs models of galaxy evolution, cluster formation, and even the thermal history of the interstellar medium. It shows that the universe is not a collection of isolated systems, but a continuous environment where energy and matter flow in feedback cycles across scales of billions of light years. The hidden oceans are not silent. They are the medium through which the cosmos breathes. As technology advances, humanity's ability to sense these faint structures improves. Future X-ray calorimeters will measure the energy of individual photons with unprecedented precision, while adaptive optics will extend Webb's reach into even fainter wavelengths. Eventually, the map of the universe may include not only galaxies and dark matter, but also the vast, luminous rivers of gas that bind them together. The discovery of these hidden oceans does not close a chapter in cosmology, it opens one. The baryons were never truly missing, they were simply waiting to be seen. Gravity shapes everything that exists, yet its most powerful architect is invisible. The visible universe, the stars, planets, and glowing nebulae that fill our telescopes, accounts for only a fraction of the total mass required to explain cosmic motion. The rest lies hidden in a form that neither emits nor absorbs light, but reveals itself through its gravitational pull. This unseen component, known as dark matter, sculpts the large-scale structure of the cosmos, dictating where galaxies form, how clusters evolve, and why the universe looks the way it does today. Without it, the familiar patterns of spiral arms, filaments, and voids would never have emerged. Evidence for dark matter first appeared in the 1930s, when Fritz Zwicky measured the velocities of galaxies within the Coma cluster and found them moving too fast to be held together by visible mass alone. Decades later, Vera Rubin's precise measurements of galactic rotation curves confirmed the mystery. Stars at the outer edges of spiral galaxies orbit just as rapidly as those near the center, contradicting the predictions of Newtonian dynamics, unless an unseen halo of matter surrounds each system. Since then, gravitational lensing, cosmic microwave background data, and large-scale structure surveys have all reinforced the same conclusion. Roughly 85% of all matter in the universe is dark. The nature of dark matter remains one of the most compelling open questions in physics. Competing hypotheses include weakly interacting massive particles, sterile neutrinos, and axions, each consistent with certain observations, yet elusive in detection. Laboratory experiments such as Xenon-NT and LU-XZEPLIN search for faint particle interactions within deep underground detectors, while astrophysical surveys look for indirect signals such as gamma-ray excesses or gravitational perturbations. So far, dark matter has refused to reveal its identity, but its gravitational fingerprints are everywhere. Every galaxy, from dwarf spheroidals to massive clusters, moves according to its hidden influence. Computer simulations have turned those fingerprints into full-fledged cosmic anatomy. Projects like Millennium, Illustrious TNG, and Bolshoi evolve billions of dark matter particles under gravity, forming intricate webs of filaments and nodes. These simulations reproduce the observed distribution of galaxies with astonishing accuracy, suggesting that baryons simply trace an underlying dark scaffold. The cosmic web emerges as a pattern of tension and release, filaments stretching across hundreds of millions of light years, connecting clusters like threads in a vast fabric. Within those filaments, gas cools, collapses, and forms galaxies. Between them, gravitational voids expand. The architecture of the cosmos is the geometry of invisible mass. JWST now allows astronomers to observe this architecture at an epoch when it was still under construction. Deep field surveys such as SEERS and JWST have uncovered galaxies less than 500 million years after the Big Bang, compact, luminous, and already gravitationally organized. Their presence supports models in which dark matter halos formed first, providing gravitational wells into which ordinary matter could fall. Without those halos, there would have been no seeds for galaxies to grow. Webb's high-resolution infrared imaging shows that even at redshifts above 10, many young systems exhibit disk-like structures aligned along filamentary flows. Gravity's blueprint was in place long before the first stars burned steadily. Weak gravitational lensing offers another window into this hidden architecture. When light from a distant galaxy passes through a foreground mass distribution, its path bends slightly, distorting the apparent shape of the background source. By measuring millions of such distortions statistically, astronomers reconstruct maps of dark matter density across the sky. The technique reveals that mass follows a filamentary pattern consistent with cold dark matter simulations. Instruments like ESA's Euclid and NASA's Roman Space Telescope are designed to chart this cosmic skeleton with unprecedented precision, connecting the invisible to the visible. The early test images from Euclid already hint at filaments stretching between clusters, confirming that what simulations predicted decades ago is manifest in nature. The influence of dark matter extends beyond large-scale geometry. It determines the morphology of individual galaxies. In disk galaxies, rotation curves depend on the distribution of dark matter halos, while in ellipticals, the velocity dispersion of stars encodes the halo's depth. Dwarf galaxies orbiting the Milky Way provide natural laboratories for testing models. Some exhibit cores, regions of relatively constant density, while others show cusps, steep central concentrations. Reconciling these differences remains a central challenge. Simulations that include baryonic feedback, energy from supernovae and black hole activity, suggest that violent outflows can redistribute dark matter, flattening central cusps into cores. Thus, even invisible mass responds indirectly to the fireworks of ordinary matter, linking microscopic physics to galactic form. Cluster-scale phenomena reveal the same duality. The bullet cluster observed in X-rays and optical light provides striking evidence for the separation of dark and luminous matter. During the collision of two clusters, the hot gas, visible in X-rays, lagged behind due to friction, while the dominant mass, mapped by gravitational lensing, passed through unaffected. The two components physically parted ways, proving that most of the cluster's mass interacts only gravitationally. Similar behavior appears in other merging systems, such as MAX J0025 and El Gordo. These cosmic laboratories demonstrate that dark matter behaves as a collisionless fluid, shaping dynamics without dissipating energy through electromagnetic processes. Recent JWST observations extend this insight to earlier epochs. In several high redshift protoclusters, galaxies appear bound together by mass far exceeding the sum of their visible contents. The infrared spectra reveal redshifts consistent with deep gravitational wells, potentially the earliest evidence of cluster assembly. These findings challenge the traditional timeline of structure formation, suggesting that massive dark matter halos coalesced sooner than expected. Whether this implies variations in dark matter properties or a revision of baryonic physics models remains an open question. Either way, gravity's invisible hand seems to have worked with remarkable speed. On smaller scales, gravitational lensing also probes dark matter's internal structure. Microlensing events, brief magnifications of distant starlight, can reveal the presence of compact dark objects such as primordial black holes. While current data limit their contribution to the overall dark matter density, they may still account for localized anomalies. In galaxy clusters, strong lensing arcs often split into multiple images, sensitive to small-scale substructure in the lensing halo. By analyzing these distortions, astronomers can infer whether dark matter is truly cold, moving slowly and clustering tightly, or warm, with enough velocity to smooth out small clumps. So far, observations favor the cold scenario, consistent with the lambda cold dark matter paradigm that underlies modern cosmology. Yet even within this framework, questions persist. Some satellite galaxies around the Milky Way are missing compared with simulation predictions, a discrepancy known as the missing satellite problem. Others exhibit densities too low for their expected halo mass, the too big to fail issue. Possible solutions include improved baryonic feedback modeling or self-interacting dark matter theories, in which dark particles occasionally collide and redistribute momentum. Such interactions could naturally soften inner density profiles and reduce small-scale clustering. Future surveys combining JWST's infrared reach with high-precision kinematics from the extremely large telescope will help discriminate among these possibilities. The cosmic web provides the stage on which these microphysical dramas unfold. Filaments not only guide galaxy formation but also channel gas inflows and outflows, regulating star formation across cosmic time. Observations using Lyman alpha emission and absorption trace these filaments around massive halos, revealing gas streaming along gravitational highways. The densest nodes host clusters whose intracluster medium glows in X-rays, heated by gravitational compression. Every layer of structure, from star-forming regions to megaparsec-scale networks, owes its coherence to gravity's subtle guidance. Dark matter, though unseen, orchestrates this coherence with mathematical precision. Understanding its nature requires bridging astrophysics and particle physics. Experiments at CERN's Large Hadron Collider search for supersymmetric particles that could act as dark matter candidates, while dedicated detectors like ADMX explore the axion hypothesis through resonant microwave cavities. In parallel, astrophysical studies look for deviations from Newtonian gravity on galactic scales, testing modified gravity theories such as MOND and TVS. So far, none have matched the explanatory power of dark matter within general relativity, but continued observation keeps the debate scientifically alive. The ultimate discovery may come from a synthesis of both perspectives, new particles confirmed in the lab and verified through cosmic signatures. Gravitational waves add a new dimension to this exploration. Collisions of massive black holes trace the distribution of matter in the early universe, and the stochastic background of low-frequency waves, soon to be mapped by pulsar timing arrays, carries information about large-scale gravitational potential fluctuations. If dark matter clumps or subhalos affect these signals, gravitational wave astronomy could become an indirect probe of the invisible. The universe speaks in gravity as well as light, and listening to both reveals its full narrative. The philosophical implication of dark matter's dominance is profound. The visible cosmos is a surface phenomenon, a thin, luminous layer floating on an ocean of shadow. Stars and galaxies illuminate the structure, but do not define it. What we see is the exception, not the rule. The true mass of the universe lies beyond sight, yet its presence is undeniable. Every orbit, every lensing arc, every filament traced by hydrogen whispers the same truth. Gravity's greatest engineer works unseen. As instruments improve, that invisibility grows less absolute. JWST's deep field imaging continues to expose the earliest gravitational scaffolds. Euclid and Roman will map the intervening cosmic web, and ground-based observatories will chart the local halos with precision unmatched in history. Together, they will refine our understanding of how the dark and luminous interact to create structure, motion, and history. The discovery of dark matter's exact nature may remain ahead, but its influence already defines the cosmos we inhabit. The universe we see is only half the story. The rest is written in gravity's invisible hand. Light is the universe's oldest storyteller. Long before atoms assembled into stars, photons were already crossing the expanding cosmos, carrying with them the memory of creation. To modern physics, light is not simply illumination, it is information encoded in quantum fields. Each photon is both particle and wave, a messenger that links the smallest scales of quantum mechanics to the largest scales of cosmology. The coherence of the cosmos, the way structure forms, persists, and evolves, depends fundamentally on the properties of light. In studying how photons behave, we glimpse how the universe organizes itself. Quantum electrodynamics describes light as an excitation of the electromagnetic field, a quantized vibration that can be emitted or absorbed only in discrete amounts. This quantization ensures stability. Atoms do not collapse because electrons occupy specific energy levels defined by their interactions with photons. Without this granularity, matter could not exist in a stable form. At cosmic scales, the same quantization governs radiation density and temperature, ensuring that the early universe cooled in a predictable pattern. The apparent order of galaxies and clusters begins with the statistical order of photons in the primordial plasma. The cosmic microwave background, first detected accidentally in 1965, is the afterglow of that plasma. It represents light last scattered when the universe was about 380,000 years old, just after electrons and protons combined to form neutral hydrogen. Before this recombination epoch, photons interacted constantly with charged particles, creating a fog of radiation. When the atoms formed, the fog cleared, and light began its 13.8 billion-year journey through expanding space. Tiny fluctuations in the CMB's temperature, only 1 part in 100,000, encode the seeds of all later structure. Quantum randomness amplified by cosmic inflation left its signature as a pattern of hot and cold spots, the first map of order written in radiation. From those minute differences emerged everything we now see. Regions slightly denser than average attracted more matter, forming the scaffolds of galaxies and clusters. But those differences would have dissipated without the stabilizing influence of radiation pressure. Photons resisted collapse, smoothing fluctuations and setting a characteristic scale known as the sound horizon, visible today as baryon acoustic oscillations. The same photons that once prevented premature collapse later became the light trapped in stars. The path from quantum fluctuation to galactic order is continuous. It is a single narrative told in changing dialects of energy. At the quantum level, light does not simply reveal reality, it defines it. Measurement in quantum theory is an interaction of photons with matter, and each interaction alters the state of what is observed. In that sense, every photon that reaches a telescope carries both what happened and how the universe allowed it to be seen. Observatories such as the James Webb Space Telescope extend this act of measurement across cosmic time. By capturing infrared photons that left their sources more than 13 billion years ago, Webb collapses quantum possibilities into visible knowledge. Each image is a record of probability resolved into history. The coherence between quantum behavior and cosmic structure suggests a deeper principle. The early universe can be thought of as a vast quantum system that decohered gradually as it expanded and cooled. Inflation magnified quantum fluctuations from subatomic scales to astronomical ones, freezing them into the density variations that shaped galaxies. In this view, the entire cosmic web is a fossil of quantum noise. The pattern of filaments and voids, now tens of millions of light-years across, began as oscillations in a field smaller than a proton. Light carried those oscillations forward, encoding them in the polarization of the CMB and in the spectra of ancient stars. Modern experiments continue to probe this connection. The Planck satellite measured the CMB's polarization with exquisite precision, confirming that its statistical properties match those predicted by inflationary models. Upcoming missions such as LIGHTBIRD and CMB-S4 aim to detect the faint B-mode polarization that would signal primordial gravitational waves, ripples in spacetime generated by quantum fluctuations of the gravitational field itself. If observed, these signals would confirm that gravity too is quantized, and that the universe's geometry has a quantum origin. The distinction between light and spacetime would then blur. Both would emerge from the same fundamental quantum fabric. At smaller scales, quantum optics provides insight into how light organizes matter even today. In star-forming regions, radiation pressure from newborn stars sculpts their natal clouds, driving turbulence and triggering new bursts of formation. In active galaxies, photons from accretion disks push against infalling gas, regulating black hole growth. These feedback mechanisms, though macroscopic, are rooted in quantum interactions between light and matter. Each photon transfers momentum, exerts pressure, and carries entropy. The collective effect of trillions of such quanta determines the structure of nebulae and the pace of stellar evolution. Photons also mediate chemistry. Ultraviolet radiation splits molecular bonds, while infrared photons carry away excess energy, allowing new molecules to form. The balance between ionization and recombination sets the physical conditions in interstellar clouds. Even the color of starlight affects the thermal equilibrium of galaxies. Blue light heats dust differently than red light, altering how gas cools and condenses. These processes illustrate how the quantum properties of photons shape macroscopic order. The color of the universe is not aesthetic, it is architectural. Cosmic order depends not only on light's energy, but on its coherence. Coherent radiation, such as that from masers and lasers, can align atomic spins and generate large-scale magnetic fields. In some galaxies, natural masers occur where molecules amplify microwaves along precise paths, revealing conditions of extreme density and temperature. Magnetic fields, in turn, guide charged particles, influencing how gas flows and stars form. Thus, coherence, a concept born in quantum optics, extends to cosmic architecture. The universe's symmetry and structure are maintained by a network of resonances, quantum coherence scaled to astronomical dimensions. At the interface of quantum mechanics and general relativity, light plays an even more profound role. In curved spacetime, photons follow geodesics that bend around mass concentrations. Gravitational lensing transforms the propagation of light into a diagnostic of geometry. When JWST observes a distant galaxy, whose light has been magnified and distorted by an intervening cluster, it is witnessing the quantum field of electromagnetism respond to the curvature of spacetime. Every photon's path encodes both the history of matter and the geometry through which it traveled. Light becomes the mediator between energy and form, turning Einstein's equations into an observable phenomenon. This interplay extends to black holes, where gravity and quantum mechanics meet most directly. Near the event horizon, intense curvature affects the behavior of virtual photons in the quantum vacuum, producing Hawking radiation. Although this emission has not yet been detected from astrophysical black holes, laboratory analogs using laser-induced horizons have demonstrated similar effects. The implication is that even the darkest regions of the universe communicate through light at the quantum level. Information may escape not as matter, but as correlations among photons, a subtle encoding that preserves the balance between entropy and order. At cosmological scales, the same principle governs entropy evolution. As the universe expands, photons stretch, losing energy but not number. The total entropy in radiation grows because space itself grows. This irreversible flow defines the arrow of time. Yet within galaxies and clusters, local gravitational collapse increases order, creating islands of complexity against a backdrop of global expansion. Light marks both directions. It redshifts with time's passage while concentrating into stars that resist it. The dual role of photons, as agents of disorder and architects of structure, embodies the fundamental tension of cosmic evolution. Recent observations illustrate this balance vividly. JWST's deep field images reveal galaxies whose infrared luminosity rivals that of entire clusters, powered by intense bursts of star formation and black hole accretion. The energy released in these systems drives winds that redistribute matter, enriching the intergalactic medium. Each photon emitted carries information about temperature, composition, and velocity. When analyzed collectively, their spectra reveal the statistical order underlying apparent chaos. The brighter the galaxy, the more clearly it expresses the universe's organizing principles. Quantum theory adds another layer: entanglement. When photons interact, they can become correlated in ways that transcend classical causality. In laboratory conditions, such entanglement persists over kilometers. In the early universe, it may have extended over light years. Some cosmological models propose that inflation froze patterns of entanglement into the large-scale structure, creating correlations between distant regions of the sky that remain measurable today. These non-local links could explain subtle anomalies in the CMB's temperature distribution. If confirmed, they would show that quantum relationships still shape the macroscopic order of the cosmos. Technological advances now allow scientists to test these ideas. Quantum sensors aboard space telescopes can detect single-photon events with extraordinary precision, enabling direct studies of cosmic background fluctuations. Experiments using superconducting detectors and photonic crystals aim to measure the polarization and energy of incoming photons with minimal noise. Each improvement reduces uncertainty, bringing cosmological observation closer to the fundamental limits imposed by quantum mechanics. Astronomy, once a macroscopic science of lenses and mirrors, is becoming a quantum science of information. This convergence redefines how we understand order itself. The universe is not ordered despite quantum uncertainty, but because of it. Randomness at microscopic scales generates diversity at macroscopic ones, allowing complexity to emerge. The same quantum noise that seeded galaxies also underlies biological and cognitive evolution. In that sense, the symmetry of the cosmos and the awareness that contemplates it are expressions of a single principle. That information, when constrained by energy and geometry, organizes itself into structure. Light is the carrier of that information, bridging the gap between chance and form. The study of quantum light, therefore, unites disciplines once thought separate. Particle physics, astrophysics, and information theory converge in a single question. How does the universe process information through energy exchange? Every photon detected by JWST, every fluctuation in the CMB, every spectral line in a distant quasar is a line in the same script. As we read that script, we uncover not only the history of the cosmos, but the logic by which it continues to evolve. The coherence of light across time and space is the coherence of the universe itself, a quantum order written in radiation. Time is the measure of change, yet change itself is bound to the flow of energy. In physics, time and thermodynamics are inseparable. The arrow of time points in the same direction as the increase of entropy. Every transformation, from the burning of stars to the cooling of the cosmic background, follows this one-way current. The evolution of the universe can therefore be read as a vast thermodynamic process, where expansion, radiation, and decay all conspire to move energy from order to disorder. But within this irreversible motion, islands of complexity arise, using local flows of energy to resist the universal drift toward equilibrium. The foundation of this connection lies in the second law of thermodynamics, which states that in a closed system, entropy can never decrease. Entropy is often described as disorder, but more precisely, it measures the number of possible microscopic configurations that correspond to a macroscopic state. A low entropy condition means the system's particles are arranged in a relatively specific way. A high entropy condition means there are countless possible arrangements. The early universe began in a state of extremely low entropy, uniform, hot, and dense, because gravitational potential had not yet been realized. As it expanded, that potential turned into structure, and entropy grew. The direction of time as we experience it is simply the direction of increasing possibilities. Radiation played the first role in setting this direction. When the universe was young, photons interacted constantly with matter, maintaining thermal equilibrium. As space expanded, the temperature dropped, and equilibrium was broken. The decoupling of light and matter, the moment when photons could travel freely, marked a profound thermodynamic transition. Energy began to flow outward irreversibly, carried by radiation whose wavelengths stretched with the expansion of space. The cosmic microwave background that JWST and Planck observe today is a fossil of that transition, its photons redshifted by a factor of 1,000, yet still preserving the imprint of the universe's initial conditions. Every subsequent epoch has deepened this thermodynamic asymmetry. Stars form when gravity overcomes local pressure, condensing gas into dense cores. This collapse converts potential energy into heat and radiation, which escapes into space, increasing entropy overall even as local order forms. A galaxy is therefore not a violation of the second law, but an expression of it, a natural engine that channels energy differences into organized complexity. The temperature difference between a star's surface and interstellar space drives chemical reactions, weather patterns, and biological evolution on surrounding planets. Life itself is a thermodynamic process that feeds on gradients. Without imbalance, nothing could change. From the perspective of statistical mechanics, the arrow of time emerges because the number of high-entropy microstates vastly exceeds the number of low-entropy ones. The universe inevitably moves from rare to common configurations. But this statistical tendency depends on boundary conditions. If the universe had started in equilibrium, no arrow would exist. The mystery is why the Big Bang produced such an extraordinarily low entropy beginning. One possibility is that inflation smoothed out irregularities while stretching quantum fluctuations into classical seeds. Another is that the laws of gravity themselves favor low entropy initial states because clumping increases gravitational entropy over time. Either way, the observed order of the cosmos implies that time's arrow was built into its birth. At the scale of galaxies and clusters, entropy increases through the conversion of mechanical and gravitational energy into heat. Collisions between gas clouds generate shock waves that radiate away energy, while black holes consume matter and emit jets that heat their surroundings. In the intracluster medium, temperatures reach tens of millions of degrees, and yet the total entropy continues to rise. Even when systems appear static, they are evolving thermodynamically. Radiation loss ensures that nothing remains perfectly stable. The universe is not simply expanding in space, but also diffusing in energy, gradually equalizing temperature differences across immense distances. Yet, equilibrium is never complete. Gravitational collapse creates local pockets where entropy temporarily decreases. These structures, stars, planets, living organisms, exist because energy flows through them. They take in low entropy energy and emit high entropy waste, maintaining internal order at the cost of increasing the disorder around them. The Earth, for example, receives concentrated sunlight and radiates infrared heat into the cold of space. The entropy of the planet itself remains nearly constant, but the entropy of the surrounding cosmos increases. In this way, complexity is the byproduct of imbalance, and time's arrow is the price of existence. As the universe ages, its thermodynamic landscape changes. Nuclear fusion in stars gradually converts hydrogen into heavier elements, releasing vast quantities of energy. Over billions of years, that energy escapes as light, which redshifts into lower frequencies as the universe expands. The mean temperature of the cosmic background continues to fall, approaching absolute zero. When star formation ceases and existing stars exhaust their fuel, only degenerate remnants, white dwarfs, neutron stars, and black holes will remain. This projected future, sometimes called the heat death, represents a state of maximum entropy where no free energy remains to perform work. Time, in the thermodynamic sense, would cease to have meaning. However, this ultimate equilibrium is far in the future, trillions of years away by current models. For now, entropy drives creation as well as decay. The same principles that will one day dissolve galaxies currently sustain them. Every photon emitted by a star represents an increase in entropy, yet those photons power new cycles of order elsewhere. Thermodynamic irreversibility is not destruction but transformation, ensuring that energy continues to flow. The universe evolves not towards stillness, but through a sequence of changing equilibria, each generating new forms of structure along the way. The concept of temperature itself acquires new meaning on cosmic scales. In general relativity, gravity influences not only motion, but thermal perception. An observer near a black hole horizon measures a higher temperature than one far away, a consequence of time dilation. The Unruh effect predicts that even space is not truly cold. An accelerating observer perceives a bath of thermal radiation. These relativistic connections suggest that time, temperature, and motion are facets of the same physical entity. Entropy increase corresponds to the passage of proper time for any system, linking thermodynamics to the geometry of spacetime. Quantum mechanics adds yet another layer. At microscopic scales, time symmetry appears preserved. The fundamental equations of physics work the same forward or backward. The arrow of time emerges only when quantum systems interact with their environments, losing coherence through decoherence. Entropy, in this sense, measures not disorder but ignorance, the loss of information about the correlations between particles. When a quantum system becomes entangled with countless degrees of freedom, its history becomes irreversible. The expansion of the universe magnifies this effect, continually increasing the number of possible configurations and thus the entropy of the whole. Black holes represent the most extreme convergence of quantum theory and thermodynamics. According to Hawking's calculations, they possess entropy proportional to the area of their event horizons, not their volume. This insight led to the holographic principle, which posits that all the information contained within a region of space can be encoded on its boundary. If true, the entire observable universe might be describable as a kind of thermodynamic hologram, a vast ledger where time's passage corresponds to the gradual writing of information on the cosmic horizon. In this framework, entropy and information are two sides of the same process, and time's flow is the updating of the universe's record. Observationally, JWST contributes to this understanding by measuring the energy output of galaxies across cosmic time. Its infrared spectra reveal how efficiently stars convert mass into radiation and how that efficiency evolves with metallicity and feedback. By integrating these data, astronomers construct an entropy budget for the universe, estimating how much free energy remains to drive structure formation. The results suggest that while the rate of entropy production peaked several billion years ago, it continues at a steady pace as smaller galaxies merge and black holes grow. Time, in the thermodynamic sense, is still flowing strongly. Some physicists propose that the arrow of time could reverse if the universe's expansion were to halt and contract. Yet current observations of dark energy imply continued acceleration. The cosmic horizon recedes faster than galaxies can communicate, isolating regions of space and freezing their thermodynamic evolution. Over vast timescales, even black holes will evaporate through Hawking radiation, releasing their stored information into an increasingly dilute bath of photons. The final state will be one of near-perfect symmetry, maximum entropy, minimum structure. The clock of the cosmos will then have ticked its last meaningful second. Still, the story of time's thermodynamics is not only a tale of endings, it also explains why structure, consciousness, and history exist at all. The universe began far from equilibrium, allowing gradients to form and persist. Those gradients power everything from nuclear fusion to neural activity. Each moment of awareness, each act of perception, consumes a tiny bit of free energy and contributes to the cosmic entropy ledger. The arrow of time is therefore not a distant abstraction, but the texture of experience itself, the physical trace of the universe's ongoing drive toward equilibrium. In the present era, humanity stands within a narrow window between cosmic simplicity and cosmic silence. Stars still shine, galaxies still merge, and information still flows. JWST's mirror, reflecting light from the earliest epochs, is effectively looking backward along the entropy gradient, seeing the universe when time's arrow was steeper and change was faster. Each observation not only reveals what was, but reaffirms why there is a was at all. The universe is a thermodynamic narrative, written in energy gradients and read in light. Time is the unfolding of that story, one irreversible second at a time. The universe expands not like an explosion, but like a fabric stretching in every direction. Each galaxy is a thread woven into that fabric, carried outward not by motion through space, but by the growth of space itself. What began as a hot, dense fireball has become a vast and nearly uniform field, its temperature diluted by 13.8 billion years of expansion. The dynamics of this expansion encode the balance between matter, radiation, and the mysterious component known as dark energy. To understand why the cosmos continues to accelerate, we must examine the architecture that drives it, the invisible geometry built into space-time itself. Einstein's general theory of relativity provides the blueprint. In his equations, matter and energy curve spacetime, and that curvature dictates how matter moves. In 1917, to produce a static universe compatible with observations of his era, Einstein added the cosmological constant, a term representing uniform energy density that resists gravitational collapse. When Hubble later discovered that galaxies are receding, Einstein abandoned the constant, calling it his greatest blunder. Yet the discovery of cosmic acceleration in the late 1990s resurrected it under a new name: dark energy. The constant he had dismissed turned out to describe the very phenomenon shaping the universe's future. Dark energy behaves unlike any known substance. Its pressure is negative, meaning it acts not as a source of attraction, but as a form of repulsion. In the standard cosmological model, it contributes about 70% of the total energy budget of the universe. The remaining 30% consists of dark matter and ordinary matter combined. While matter slows expansion through gravity, dark energy pushes it faster, and because its density remains constant while matter thins out, its influence grows with time. The result is a universe whose expansion rate increases even as its contents become more diffuse. Space itself carries an intrinsic tendency to stretch. Observationally, this acceleration manifests in multiple ways. Type 1a supernovae serve as standard candles, their brightness revealing distances and confirming that faraway galaxies are receding faster than expected. Measurements of the cosmic microwave background show a geometry that is spatially flat, implying a delicate balance between total energy density and curvature. Large-scale surveys of galaxies detect subtle imprints of baryon acoustic oscillations, fossil sound waves from the early plasma, which act as rulers to track how the expansion rate changes over time. Together, these data converge on a consistent picture, a cosmos dominated by a uniform energy field permeating every cubic centimeter of space. What that field actually is remains unknown. The simplest interpretation treats it as a property of the vacuum itself, the zero-point energy predicted by quantum field theory. Virtual particles constantly appear and disappear in empty space, giving the vacuum a measurable energy density. However, theoretical estimates exceed observed values by a factor of 10 to the 120 power, the largest discrepancy between theory and experiment in all of physics. Resolving this cosmological constant problem is one of the great challenges of modern science. Some theories propose that the vacuum energy is canceled almost completely by unknown symmetries, leaving only a tiny residual that drives the observed acceleration. Others suggest that dark energy evolves, arising from a dynamic scalar field called quintessence. Each hypothesis alters the architecture of expansion in subtle but testable ways. JWST contributes to this investigation by measuring the ages and luminosities of distant galaxies, providing independent constraints on how fast the universe expanded in earlier epochs. Combined with data from Euclid and the Roman Space Telescope, these observations will refine the Hubble constant and clarify whether cosmic acceleration is perfectly smooth or varies across space. If deviations appear, they could indicate that dark energy interacts with matter or that general relativity breaks down on the largest scales. Cosmology, once dominated by geometric simplicity, is now a frontier of experimental precision. The expansion itself is not merely kinematic, but thermodynamic. As space stretches, photons lose energy, their wavelengths increasing in direct proportion to the scale factor. This redshift transforms the high-frequency radiation of the early universe into the faint microwave background observed today. Entropy grows because energy becomes less available for work. The process is irreversible. No mechanism can reconcentrate cosmic light once it has been diluted by expansion. Every second that passes increases the horizon volume and spreads information thinner, embedding the arrow of time into the metric of space itself. At intermediate epochs, the competition between gravity and expansion produced a rich diversity of structure. Galaxies condensed along filaments, clusters merged, and supermassive black holes anchored the centers of growing systems. Feedback from stellar winds and active galactic nuclei redistributed energy, shaping morphology and regulating star formation. Yet, as acceleration continues, gravitational binding will lose its reach. In 100 billion years, distant galaxies will recede beyond our cosmic horizon, their light stretched so far that it fades into darkness. The observable universe will contract in informational terms even as physical space expands. Future observers, if any remain, will see only their local group of galaxies, isolated in an ever-deepening void. This fate raises questions about meaning in physical terms. What does expansion aim toward? In thermodynamics, equilibrium is not a goal but a consequence. The same is true for the cosmos. The universe expands because that is the configuration in which energy distribution most naturally progresses. The geometry of space-time adjusts to balance density and pressure, and when that balance favors negative pressure, acceleration follows. Expansion is therefore not an explosion, but the spontaneous relaxation of the universe toward its lowest energy configuration, guided by Einstein's equations as surely as heat flows from hot to cold. The long-term outcome depends on the precise value of dark energy's equation of state parameter, denoted W, which relates pressure to energy density. If W equals -1 exactly, the acceleration will continue indefinitely, leading to a cold, exponentially expanding universe. If W is less than -1, a scenario known as the Big Rip may occur, where the repulsive force grows without bound, tearing apart galaxies, stars, and eventually atoms themselves. If W is greater than -1, expansion will slow and perhaps reverse into a big crunch. Current measurements favor -1 within a few percent, suggesting that dark energy behaves like a true cosmological constant. Yet even small deviations could alter the ultimate architecture of existence. From the standpoint of information theory, expansion performs a continual computation. Each horizon volume represents a finite number of bits, determined by its surface area in Planck units according to the holographic principle. As the universe expands, the total information capacity increases, but the information density decreases. The cosmos is writing its own history on an ever-growing canvas, each quantum of light adding another line to the record. The irreversible growth of that record corresponds to the passage of time. Entropy, information, and expansion are three expressions of the same underlying process: the conversion of energy into geometry. On the scale of human experience, these principles manifest in subtler ways. Every observation, every experiment, depends on photons that have traveled across expanding space. The finite speed of light means we always see the past, never the present. The act of looking outward is the act of looking backward, tracing the gradient of entropy that defines time itself. When JWST captures an image of a galaxy from 13 billion years ago, it is not just collecting data, it is sampling the slope of the universe's expansion, reading the curvature of space-time through light. Our awareness of cosmic history is a direct consequence of the way expansion stretches both space and time. The expansion also imposes limits on knowledge. Beyond the cosmic horizon lies a region forever inaccessible to observation, not because it does not exist, but because its light will never reach us. In physical terms, the horizon defines the boundary of causality. The number of observable events is finite, even though the universe may be infinite. This limitation is not a flaw, but a structural feature of space-time's architecture. It ensures that the universe remains consistent with relativity. Information cannot travel faster than light, and geometry enforces that law universally. The edge of the observable cosmos is thus the ultimate expression of order emerging from constraint. Despite its inevitability, cosmic expansion is not a slow death, but a dynamic equilibrium between creation and dilution. New stars still form, black holes still merge, and matter still cycles through stages of complexity. The energy released in these processes adds to the cosmic background, ensuring that the story of light continues. On vast timescales, galaxies will evolve into diffuse halos, stars will fade into embers, and the last photons will drift through a near-perfect vacuum. But even then, quantum fluctuations will persist, ensuring that absolute stillness remains unattainable. The universe's final state may be quiet, yet never silent. In the grand chronology of existence, expansion serves as both stage and script. It transforms quantum uncertainty into cosmic structure, thermodynamic imbalance into evolution, and gravitational curvature into history. Every epoch, from the Rionization era to the modern age, fits within this architecture, each layer built upon the last. The same physical laws that govern atomic transitions govern the motion of galaxies, unified by the mathematics of energy conservation and symmetry. The cosmos is not chaotic but coherent, bound by rules that remain invariant even as scales change by 30 orders of magnitude. As science advances, our capacity to model this coherence improves. Supercomputers now simulate the evolution of billions of particles across billions of years, reproducing the observed large-scale distribution of matter with striking fidelity. These simulations reveal that even randomness obeys order when guided by gravity and expansion. Filaments form where equations predict, voids appear where density falls below threshold, and the geometry of space-time itself emerges as a dynamic solution rather than a fixed backdrop. The universe is not expanding into emptiness. It is creating the conditions of space as it expands. In this realization lies a quiet kind of closure. The journey from the first light to the accelerating cosmos has revealed not chaos, but consistency, a continuous thread connecting quantum mechanics, thermodynamics, and general relativity. Each law is a translation of the same underlying logic. Energy transforms, information increases, and geometry responds. Time is not an external river flowing through the universe. It is the measure of these transformations within the universe. Expansion is simply the shape that time takes when viewed through the lens of space. Eventually, all gradients will flatten, all structures will fade, and only the faint hum of stretched photons will remain. Yet the memory of every interaction, the record inscribed in the fabric of space-time, will persist. The universe will not end in silence, but in perfect symmetry, a final equilibrium that contains the trace of everything that came before. From the first quantum fluctuation to the last ripple of light, the cosmos will have completed its long experiment in complexity. The expansion of space will have been the mechanism through which energy learned to remember itself. In that sense, the universe does not simply expand, it learns. Each epoch refines the relationship between matter and law, between possibility and realization. The architecture of expansion is the architecture of understanding, a structure built not by intention, but by necessity, one that converts entropy into meaning. To study it is to glimpse the logic that underlies existence, the equation that binds motion to memory and turns time into history. The cosmos continues to unfold, not toward a goal but toward expression, and in that unfolding lies both its mystery and its truth.